Welcome to this section on collection. In this section, we will learn how we can move data into AWS. Now, there's a lot of ways to move data into AWS, and I like to segment it into three different categories. The first one is for real-time collection, where we can perform immediate action on our data. For this, we'll go over Kinesis data streams, Simple Queue Service or SQS, and IoT for Internet of Things. All these services allow you and your applications to react in real time to events or data that is happening in your infrastructure. Now, there's a second way of collecting, which is near real time, which is more for reactive action instead of immediate. So what does near real time mean? Well, it means you will use Kinesis Data Firehose, and don't worry, all these things will visit them in this section, or the database migration service. Finally, there's a third kind of collection, which is not very close to real time. It's called batch. And this is usually called when you want to move large amount of data for historical analysis into AWS, maybe to do some big data analysis on it. This is the course, right? So we have Snowball and Data Pipeline. So all these services will be described in this section. There's a lot of things to learn, but I hope you get a general picture of where things stand in terms of real-time, near real-time, and batch, and we'll see you in the next lecture. So the first service you need to know about is Kinesis Data Streams. And Kinesis Data Streams is a way for you to stream big data in your systems. So a Kinesis Data Stream is made of multiple shards. And shards are numbered, number 1, number 2, all the way to number n. And this is something you have to provision ahead of time. So when you start with Kinesis Data Streams, you're saying, hey, I want a stream with 6 shards. And so the data is going to be split across all the shards, okay? And the shards are going to be defining your stream capacity in terms of ingestion and consumption rates. So for now, let's just start with this. And then we have producers. So producers send data into Kinesis Data Streams. And producers can be manifold. They could be applications, they could be clients such as desktop or mobile clients. They could be leveraging the AWS SDK at a very, very low level, or the Kinesis Producer Library KPL at a higher level. And we'll have a deeper dive onto the producers in the next lectures. Or it could be the Kinesis agent installed on the server to stream, for example, application logs into Kinesis Data Streams. So all these producers do the exact same thing. They rely on the SDK at a very, very low level, and they're going to produce records into our Kinesis data stream. So a record at its fundamental is made of two things. It's made of a partition key, and it is made of the data blob or the value that is up to 1 megabyte. So the partition key will define and help determine in which shard will the record go to, and the data blob is the value itself. So when you have the producers sending data to Kinesis Data Streams, they can send data at a rate of 1 megabytes per second or 1,000 messages per second per shard. So if you have 6 shards, you get 6 megabytes per second or 6,000 messages per second overall, okay? Now, once the data is in Kinesis Data Streams, it can be consumed by many consumers. And these consumers, again, can have many forms, and we'll explore them in details in this section. So we have applications, and they could be relying on the SDK, or at a high level, the Kinesis Client Library, so KCL. There could be Lambda functions if you want to do serverless processing on top of Kinesis Data Streams. It could be Kinesis Data Firehose, as we'll see in this section, or Kinesis Data Analytics. So when the consumer receives a record, it receives again the partition key, also a sequence number, which represents where the record was in the shard, as well as the data blob, so the data itself. Now we have different consumption modes for Kinesis Data Streams. We have 2 megabytes per second of throughput shared for all the consumers per shard, okay? Or you get 2 megabytes per second per shard per consumer if you are enabling the enhanced consumer mode, the enhanced fan out. So we will look at it again in this section in greater detail. So again, producers send data to Kinesis Data Streams. It stays in there for a while, and then it is read by many different consumers. Okay, some properties of Kinesis Data Streams. The first one is that retention can be set between 1 day to 365 days. And that means that by default, you have the ability to reprocess or replay data. And once data is inserted into Kinesis, it cannot be deleted. That's called immutability. Also, when you send messages to Kinesis Data Streams, you add a partition key. And messages that share the same partition key will go to the same shard, and that gives you key-based ordering. For producers, you can send data using the SDK, Kinesis Producer Library, KPL, or the Kinesis agent. And for consumers, you can write your own. So Kinesis Client Library, KCL, or the SDK, or you can use a managed consumer on AWS, such as AWS Lambda, Kinesis Data Firehose, or Kinesis Data Analytics. Now for capacity modes, you have two options for Kinesis Data Stream. The first one, that's the historic capacity mode. It's called provisioned mode. So you choose a number of shards provision, and then you can scale them manually or using an API. And each shard in Kinesis Data Streams is going to get 1 megabyte per second or 1,000 records per second. And then for the out throughput, each shard will get 2 megabytes per second. And this is applicable to classic or fan-out consumer. You also pay per shard provision per hour. So you need to think a lot in advance, and it's why it's called provision mode. But the second mode is a newer mode called on-demand mode. And in this, you don't need to provision or manage the capacity. That means that the capacity will be adjusted over time on demand. You get the default capacity provision, which is 4 megabytes per second or 4,000 records per second. And then there will be automatic scaling based on the observed throughput peak during the last 30 days. And in this mode, you're still going to pay per stream per hour and per data in out per gigabyte. So a different pricing model. So if you don't know your capacity in advance, go for on demand. But if you can plan capacity in advance, you should go for provisioned mode. In terms of security for Kinesis Data Streams, it is deployed within a region. And so you have your shards. You can control access to produce and read from the shard using IAM policies. There is encryption in flight using HTTPS and encryption at rest using KMS. You can implement your own encryption and decryption of data on the client side, which is called client-side encryption, and it is harder to implement because you need to encrypt the data yourself and decrypt it yourself, but this enhances security. VPC endpoints are available for Kinesis. This allows you to access Kinesis directly from an EC2 instance in a private subnet without going through the internet. And finally, all the API calls can be monitored using CloudTrail. So that's it for an overview of Kinesis Data Streams. I hope you liked it, and I will see you in the next lecture for a deeper dive on all the moving parts in Kinesis Data Streams. So we need to know how we can produce data into Kinesis. So here is our Amazon Kinesis Streams, and the exam will expect you to know at a high level how each of these work. The first one is the SDK. The SDK allows you to write code or use the CLI to directly send data into Amazon Kinesis Streams. The second one is to use the Kinesis Producer Library, or KPL. Remember that acronym. The Kinesis Producer Library is going to be a bit more advanced. You're going to write better code, and it has some really good features that I will describe in this lecture, which allow you to get enhanced throughput into Kinesis Streams. The third one is to use a Kinesis agent. So the Kinesis agent is a Linux program that runs on your server. So remember that, it's an agent that runs on servers and basically allows you to get a log file, for example, and send that reliably into the Amazon Kinesis Streams. Finally, you can use third-party libraries that usually build upon the SDK, such as Apache Spark, Kafka Connect, NiFi, etc. And all these things will allow you to send data to Kinesis Streams reliably. So look at this diagram. Remember that Kinesis Streams can have different ways of getting data from various sources. Now let's do a deeper dive into all the methods on the left-hand side. So the first one is to use the Producer SDK, and that uses the put record or put records with an S API. So anytime you see put record, that means SDK. So with the put record, as the name indicates, you send one record, and if you use put records with an S, you will send many records. Put records will use batching and therefore increase your throughput. That's because you send many records as part of one HTTP request, and therefore you're saving in HTTP request and getting increased throughputs. Now, if you do go over your throughput though, you will get a provision throughput exception exceeded, and that's important to know how to deal with this. We'll see this in the very next slide. Now, this Producer SDK can be used on various different ways. You can use it on your applications, but also on your mobile devices, such as Android, iOS, etc. So when would we choose to use the Producer SDK? Well, anytime we have some low throughput use case, or we don't mind a higher latency, we want a very simple API, or maybe we're just working straight from AWS Lambda. This is the kind of places where you would use the Producer SDK. You need to know as well that there are some managed AWS sources for Kinesis data streams. So they, behind the scenes, use a producer SDK, but you don't see it. And so these managed sources are going to be CloudWatch logs, so you can send your logs directly from CloudWatch into Kinesis. You have AWS IoT, and we'll see this in this section. And finally, Kinesis Data Analytics is able to produce back into Kinesis data streams. So remember that. Now, how do we deal with exceptions for the Kinesis API? Well, if you get a provisioned throughput exception, that happens when you are sending more data than you can. For example, you're exceeding the number of megabytes per second, or you're exceeding the number of records per second you can send to any shard. So you need to make sure when you get this that you don't have a hot shard. For example, if you have device ID as your key and you have 90% of your devices being iPhones, then you're going to get a hot key, a hot partition, because all your devices are iPhones and they will all go to the same partition. So make sure you distribute as much as possible your key that you choose in order not to get a hot partition. So solution is, if you get a provision throughput exception, try to do retries with backups. That means that you will retry after maybe 2 seconds, and if it doesn't work, you will try after 4 seconds, and then after 8 seconds. They're just like arbitrary numbers. Or you can increase the number of shards you have in Kinesis, basically to increase the amount of scaling you can do. And you need to ensure that your partition key is a good one, a very distributed one. So for example, for the mobile device, instead of choosing Apple versus Android, you would choose maybe the device ID, which for sure is going to be different for each of your users. Just an example. So now let's talk about the Kinesis Producer Library, or KPL. You need to learn exactly how this works because this is very important going into the exam. It's an easy to use and highly configurable C++ or Java library. And personal experience, I've seen Java being used more when you use the KPL. It's used when you want to build high performance, long running producers. And it has automation for the retry mechanism. So the exception I just described before, which we have to deal with when using the API, well, the Kinesis Producer Library automatically knows how to deal with this. Now, Kinesis Producer Library has two kinds of APIs. There's synchronous API, which is the same as the SDK, or asynchronous API, which will provide you better performance. But you need to deal with asynchronicity, obviously. So every time in the exam you see, okay, we need to send data asynchronously to Kinesis data streams, usually the Kinesis Producer Library, or KPL, will be the way to do it. It's a really nice library because it also is able to send metrics to CloudWatch for monitoring. So anytime you write an application with a KPL, you can monitor it directly in CloudWatch. And it supports a very important mechanism called batching. And batching has two subsections, and they're both turned on by default, and they will help you increase the throughput and decrease the cost. You need to know those, absolutely. The first one is to collect records and write to multiple shards in the same put records API call. And the second one is to aggregate, which increase the latency but increase the efficiencies as well. So it's the capability to store multiple records in one record, and you're able to go over the 1000 records per limit with this. I'll describe these to you in the very next slide anyway. And that will allow you to increase the payload size and therefore increase throughput, so you can reach that 1 megabyte per second limit more consistently. If you want to use compression, so that means make your records smaller, then this is not something the Kinesis Producer Library supports out of the box, unfortunately. You would have to implement this yourself. When we do send a record with the Kinesis Producer Library, though, it's a very special record and you cannot just read it using the CLI. For this, you would need to use the KCL or a special helper library, and we'll see the KCL in the next lecture. So let's talk about this batching because this is such an important concept to understand in Kinesis Producer Library and something the exam will ask you about. So here's, for example, me sending a record to Kinesis, and it's 2 kilobytes, and I'm sending it using the Kinesis Producer Library. Turns out it's not going to be sent right away. It's going to wait a little bit of time to see if more records are coming in. And maybe I'm sending a next record of 40 kilobytes. Maybe I'm sending a next record of 500 kilobytes. And what Kinesis Producer Library will do is that at some point it will say, wait a minute, I can aggregate all these records into one record. So instead of sending 3 records, now we're sending 1 record, and that record is still less than 1 megabyte. And so we're going to do this in multiple times. So maybe we're going to have 1, 30, 80, and 200 kilobyte again, and it's going to aggregate that one as well into 1 record. So now we have 2 records. So we've seen what aggregation is. And then it's going to say, wait a minute, now we have to send 2 big records, but we're not going to use 2 put record API. We're going to use one of them, and we'll do collection. So we'll use the put records API. So here you see I wanted to send 7 records to Kinesis, and I end up doing only one API call because we have aggregation and collection. And so how does Kinesis know how long to wait to batch these records? So you can control it using this record max buffer time, which defaults to 100 milliseconds. Basically, you're saying, okay, I'm willing to wait 100 milliseconds, so that's adding a little bit of latency at the trade-off of it being more efficient. So if you want less delay, you would decrease that setting, and if you want more batching, you would increase that setting. So that's it for the KPL. Just remember the batching mechanism, it's really important. So there is one situation where you may not want to use the Kinesis producer library, and this is something that can come up in the exam. So when you use the KPL, you can incur an additional processing delay of up to record max buffer time. So this is a user configurable setting within the library. And the idea is that the longer you have this buffer, so the larger value for that record max buffer time, means that you will have higher packing efficiencies and better performance because more records will be accumulated in that buffer and they will be sent as one larger record, which will be more efficient, potentially compressed, and so on. But if you have an application that cannot tolerate an additional delay, then you may need to use the AWS SDK directly. That means you want to send the data right away. So let's take an example. If you have an IoT sensor and it comes with the AWS SDK and you want to produce to Kinesis data streams, but that IoT sensor sometimes is offline. So if you use the KPL and there is an offline event, what's going to happen is that the KPL will keep the data and accumulate it. And so that means that when my device goes back online, it may take a little bit of time for the latest data to arrive into my Kinesis data stream. And maybe we just want to act upon the latest data. So in that case, instead of using the KPL, it would be more sensible for us to implement our applications directly using the SDK API calls named put records. Because when we use put records, we can choose to discard all data and we can choose to send only the latest, most relevant data when my device is online. So now you know that use case and it can come up in the exam. Last way to produce to Kinesis is to use the Kinesis agent. And so this agent will basically be installed and it will monitor log files and directly sends them to Kinesis data streams. It's just a configuration to do. It's a Java-based agent and actually it's built on top of the KPL library. That makes it really reliable and efficient. You would install this only in Linux-based server environments for now. So the features is to write from multiple directories and write to multiple streams. It has a routing feature based on the directory or log file you're using. And it can even pre-process the data before sending it to Kinesis data streams. It can do single line divisions, it can do CSV to JSON, log to JSON, and on top of it, the Kinesis agent is really well written, so it will handle anything like log file rotation, checkpointing, and retry upon failures. And because it uses the KPL library, then it will emit metrics to CloudWatch for monitoring. So anytime you need to do aggregation of logs in mass, in almost real time, then the Kinesis agent is the way to go. All right, so we've seen all the ways to produce into Kinesis. I know that's a lot, but remember, at a high level, you need to understand how they work, and I hope I've achieved just that. I will see you in the next lecture. Now let's talk about how we can consume data from Kinesis data streams. And we'll talk first about the classic consumers. So the first one is the Kinesis SDK. So the same way we could use the CLI or some programming language to push data to Kinesis data streams, we can use the SDK or the CLI to read data from Kinesis data streams. We can also use the Kinesis client library, and I hinted at it in the previous lecture. It's named KCL. So we produce with the KPL and read with the KCL. There's also the Kinesis connector library, which could be abbreviated to KCL, but actually isn't, so it's a bit different from consumer client library. And then we have third-party libraries, such as Apache Spark, Log4j, Flume, Kafka Connect, all these things. But the exam expects you to know that Apache Spark is able to read from Kinesis data streams as a consumer. We can also use Kinesis Data Firehose and also AWS Lambda if we need to. There's this mechanism of consumption called Kinesis Consumer Enhanced Fanout, and I will discuss it in the next lecture. So for now, let's just consider how a classic consumer would work on Kinesis. So first, the SDK, get records. So this is classic Kinesis, and that means that the records are going to be pulled by the consumer from a shard. And each shard will get a maximum of 2 megabyte total of aggregate throughput. So each shard, remember, 1 megabyte of producer, 2 megabytes of consumer. So here's the example. Our producer is producing to our Kinesis data stream, and it's formed maybe of, let's say, 3 shards. And so if we have 3 shards, then we have 6 megabytes of aggregate throughput for downstream. But each shard itself will get 2 megabytes for its own. So now we have a consumer application, and it wants to read from, for example, shard number 1. What it will do is that it will do a get records API call, and the shard will return some data. And if the consumer wants more data, it needs to do another get records API call. So that's why it's called a polling mechanism. So get records, every time you run it, it will return up to 10 megabyte of data. And then because that 10 megabyte of data goes over the 2 megabyte per second total, you will need to wait 5 seconds until you do another get records. Or it will return a maximum of up to 10,000 records. Now that means, what is that? There's also another limit you need to know. First, it's that there's a maximum of 5 get records API calls per shards per second. So that means that your consumer application, it cannot do just get records like 20 times per second. It can do it only 5 times per second. That means that you will get 200 millisecond latency on your data. So remember that number because it's really important. But now what does that mean? If we look at these constraints and we start adding more consumers, well, if 5 consumers' applications consume from the same shard, they're different applications and they all need to read the same data, then each consumer basically can poll for once a second and can receive less than 400 kilobytes per second. So that means that the more consumers you have, the less throughput you will have per consumer. So if we had consumer B and consumer C, they will all share that limit of 2 megabytes per second per shard, and they will all share that limit of 5 get records API call per second. So it's really important to understand that, and we'll see how Kinesis Enhanced Fanout for consumers will solve that problem. So the next thing we're going to explore is the Kinesis client library. And it is a Java's first library, but it exists as well for other languages too, such as Golang, Python, Ruby, Node, and .NET. And the idea is that using the KCL, you can read records from Kinesis produced with the KPL because it has a de-aggregation mechanism within the library. It also has the possibility to have multiple consumers share multiple shards using the concept of a group. And that means that there is a shard discovery process included in the KCL. Also, there's a checkpointing feature in case your applications go down or your records processor go down, then they can resume from wherever they were last processing. It also leverages DynamoDB for the coordination and checkpointing. So that means that there's going to be new DynamoDB, 1 row per shard. And so that means that because DynamoDB is involved in the process to read from a Kinesis data stream, that means that you need to take care of your provisioning of your DynamoDB table. That means that you need to have enough write capacity units, so WCU, and read capacity units, so RCU. Or if you just don't want to worry about it, you can use the on-demand mode for DynamoDB and not get any throttling exception. Because in case you have exceptions on your DynamoDB table, then DynamoDB will throttle and then may slow down your Kinesis client library to read from Kinesis itself. Now, record processors will process the data. And then if you get, as I said, an expired iterator exception, that means that something is going on in your KCL library. That means that you need to increase the WCU because your DynamoDB table is not fast enough to keep up with the writes. So this is an exam question. So let's have a look at how it works. So we have a Kinesis data stream and it has maybe 4 shards. And we have a DynamoDB table that will be used for the checkpointing and coordination of our KCL record processors. So in this example, I have 2 KCL applications of the same group running on 2 different EC2 instances. And so thanks to this shard discovery mechanism where they can share the shards, so the first one will be reading from shard 1 and 2, and the second one will be reading from shard 3 and 4. And then the KCL applications will be checkpointing the progress into the DynamoDB table. And this happens quite often. That means that you need to provide enough WCU for your DynamoDB table. And again, in case you get an expired iterator exception, you need to increase the WCU, your write capacity units, on your DynamoDB table. There's also the utterly confusing connector library, also known KCL, but Kinesis Connector Library, and it's an older Java library from 2016, and it leverages the KCL library under the hood, and it's used to write data to Amazon S3 or DynamoDB, Redshift, or Elasticsearch. And the connector library must be running on an EC2 instance, for example, for it to happen. So it's an application whose sole purpose is to take data from Kinesis data streams and send it to all these destinations. Now, you may be like, oh, this is already something we can do with Kinesis Firehose, and that's true. We can already do this with Kinesis Firehose, and we'll see this. So for some of these targets, we can use Kinesis Firehose, for example, for S3 and Redshift. But for others, we can use AWS Lambda. So overall, I would say the Kinesis connector library can appear at the exam, but it's kind of deprecated and replaced by Kinesis Firehose and Lambda altogether. So let's talk about Lambda now. Lambda can read records from a Kinesis data stream. And the Lambda consumer also has a small library, which is really nice, used to de-aggregate record from the KPL. So you can produce with a KPL and read from a Lambda consumer using a small library. Now, Lambda can be used to do lightweight ETL. So we can send data to Amazon S3, DynamoDB, Redshift, Elasticsearch, or really anywhere you want, as long as you can program it. And Lambda can also be used to read in real time from Kinesis data streams and to trigger notifications, or for example, send email in real time, or whatever you may want. Finally, Frank will describe this at length, but there is a configurable batch size, and we'll see this in the Lambda section. But basically, you can say how much data at a time Lambda should read from Kinesis, which helps you regulate throughputs. So overall, we've seen all the ways we can read from Kinesis data streams. There are many different ones, but hope it places some context to which one is good for which use case. And I will see you in the next lecture. So let's go ahead and get some practice for Kinesis data stream. So I'm going to open the Kinesis service and create our first Kinesis data stream. So as we can see, we have three options here. We can use data streams, data firehose, or data analytics, but we only know about data streams so far. So let's go ahead. We get some information around the pricing, which is that per shard, we pay $0.015 per hour. Okay. And then there's a cost for making puts or for sending data into Kinesis data streams. So we'll create a data stream. Let's name our stream demo stream, and then we have to define the data stream capacity. So as you can see, we have two modes. We have the on-demand mode and the provision mode. And in the on-demand mode, you don't have to think about the capacity. It's automatically going to scale for you. So there's a maximum throughput of 200 megabytes per second and 200,000 records per second, and a maximum read capacity of 400 megabytes per second per consumer if you're using the enhanced fan-out option. So the on-demand has a pay-per-throughput pricing model, but there's no free tier, okay? And the provision mode also doesn't have a free tier. And in the provision mode, you need to provision shards. And so there's a shard estimator tool if you wanted to understand how many shards you needed based on like how many records you send per second and what is the size of your record and how many consumers you have, okay? But in our example, we're going to just set up one shard. One shard gives us 1 megabyte per second for write and 2 megabytes per second for read. And obviously, if you put 10 shards, then everything is multiplied by 10, okay? And so one shard is enough for us to do the demo. It's also the cheapest option we can get. If you do not want to pay any money in this course, then do not do this hands-on because you will pay some money for your shard. Although we will deal with it and then delete it fast enough. So when you're ready, you just click on Create Data Stream and you wait for the data stream to be created. And our stream is now successfully created. So in terms of applications, we can see we have producers and we are recommended three options: the Kinesis agents, the SDK, or the Kinesis producer library. So they're all available on GitHub for you to check it out. This is a way to stream data from application servers into Kinesis data streams. The SDK is for you to develop producers at a very low level, and the KPL is for you to develop producers at a very high level with a better API. And in terms of consumers, we get Kinesis Data Analytics, Kinesis Data Firehose, or the Kinesis Client Library, or Lambda as well. That is not shown as an option right here. Okay, we get some monitoring information about our Kinesis data stream, so how many records we are sending into it. We could look at the configuration. So if we wanted to scale the stream, we can say how many shards we want. We can go from 1 to say 5 and scale our Kinesis data stream. We could add some tags, and then we could use enhanced fan-out and configure it if we wanted to have some consumer applications leveraging the enhanced fan-out capability. But for now, let's keep it simple. We just want to write and read from our stream. And so therefore, we want to use the SDK for producing and for consuming. So to do so, we want to open a CLI, and let's use Cloud Shell because it's fun. So I'm going to click on Cloud Shell right here, which is the icon next to the bell icon. And this is going to open, for me, a command line interface in AWS. As an alternative, you could be using your own terminal or CLI if it's pre-configured, but I like to switch things up, and this one I really like because there's less configuration involved at least. Creating the environment the first time can take a bit of time, and the Cloud Shell is free on AWS, so no worries here. In the meantime, on Kinesis, open the Kinesis data streams.sh file, and we're going to use that overall. So there are two types of commands to write to Kinesis data stream based on your CLI version for the AWS CLI. So usually you have version 2 installed, but it is possible for you to somehow have version 1 installed. And so to get the version, you just type AWS version and paste, and then you will get some information around the version of AWS CLI. So on Cloud Shell, the CLI version that's going to be installed is version 2, as you can see here, AWS CLI version 2.1.16. So we're going to use the CLI commands version 2. But if you wanted to have the version 1, then you would use these commands. Okay, so now we're good to go. The first thing we want to do is send a record into our Kinesis data stream. And to do so, there is an API called put record. And put records, we need to specify a stream name. So in this example, I didn't name my stream test. I named it demo stream. So we'll have to change this in the CLI command, but you get the idea. Then you specify a partition key for the data you're sending. So user 1, and remember the data that shares the same partition key will go to the same shard, but we only have one shard, so that doesn't matter in this case. Then the data itself, so user sign up. And finally, because we are writing some text data, we need to say this option, CLI binary format, raw in, base 64 out. Okay, so let's paste this command, so copy and paste, but let me just edit the stream name to make sure that it is demo stream. And the Cloud Shell is automatically configured with your own IAM credentials, so it will inherit whatever you have for IAM credentials, and also will use the region by default in which it was launched, so US East 1. I press enter, and now we get a successful message. So the message was sent to shard ID 000000, so our first shard, and the sequence number of the message is here. If I do it again, then I'm going to get a second message with a successful. So we can do user sign up, we can mix up the message, then user login, and then maybe user logout. So we're just sending a few messages into our Kinesis data stream. Perfect. So I'm going to clear this. And if you waited a little bit and went into monitoring and look at the stream metrics, I will have it on 1 hour, you would see a put record right here. But it takes a bit of time for CloudWatch metrics to be updated, but you would see it here. Okay. So next, we want to be able to consume from our Kinesis data stream. So to do so, we're going to first describe the stream to get some information around what the stream is made of, because we need to be able to consume from a specific shard. So it's demo stream. I'll press enter. And as you can see here, we have the stream description. We have one shard called shard ID 00000. And so we need to keep this in our mind, okay, to be able to read from the stream. And so when you use the CLI, the SDK at a very, very low level, you need to specify from which shard you are reading from. But if you're using Kinesis client library, all of this is handled for you by the library itself. But we are using the CLI, so we have to specify the shard ID. So I press Q to quit this, and I'm going to consume some data. So I'm going to run this command right here. And let me clear this. And there's two things to note. So number one, I need to change the name of the stream I'm consuming from. So demo stream is the stream. And then the shard iterator type is stream horizon. And this means that you're going to read from the very beginning of the stream. So it will read all the records that were sent from the beginning. The other option, just make sure you only receive the records from that very moment onwards from when you launch the CLI command. Anyway, so I'm going to press enter, and this is going to give me a shard iterator. And this shard iterator can be reused to consume records. So the next API command is Kinesis get records shard iterator, and then we just specify this entire string right here. So this consumption mode I'm doing right now by using the low-level API, describing the stream, getting a shard iterator, and getting records is using the shared consumption model. This is not using enhanced fanout, which in my opinion should be using the Kinesis client library, consumer library, for you to really leverage and have a nice API to do so. But this is low level. So let's click and let's press enter on the Kinesis get records, and we get a batch of records out of it. So we have record 1 right here, which is partition key user 1. And we have some data right here, but it's base 64 encoded. We have, again, another data base 64 encoded. We get some timestamp information, another data base 64 encoded. And then if I press enter, it's going to go a little bit down. Some more data that is base 64 encoded. So to just make sure we can read the data, I can go to website base 64 decode online. And I'm going to just paste this data right here into base 64 decode and click on decode. And this gives us user sign up. And if I paste the second type of data, this one, copy and paste it in here, this is going to give us user login, so which is the data we sent. So that's perfect. Everything is working. And then as you can see, there's a next shard iterator argument right here. So the next time we consume, we need to specify this next shard iterator argument to consume from where we stopped consuming from. So this is something you have to iterate from in your code. But at a low level, we've produced data to Kinesis data stream and consumed data from Kinesis data stream, which is awesome. And we've also used Cloud Shell in the meantime, which I think is very handy. So that's it for this demo. Just keep the stream open as we will be using it for Kinesis Data Firehose in a second. And I will see you in the next lecture. So I like to make sure I teach you about real-world big data, not just exam big data. And even though this might not be an exam just yet, I think it will appear very soon. And to me, Kinesis Enhanced Fanout is what I call a game-changing feature. And it was appearing in August 2018, so I'm sure it will be in the exam very, very soon anyway. So how do we leverage this? Well, it will work if you use KCL 2.0 or AWS Lambda from November 2018. So it's supported by both these things. And what does Enhanced Fanout mean? That means that each consumer will get 2 megabytes per second per shard. So it looks similar as before, but it's not exactly the same, right? So we have a producer producing to a Kinesis data streams and has, for example, one shard in this example. We'll have a consumer application A, and we'll do an API called subscribe to shard, and automatically Kinesis data stream will start pushing data at the rate of 2 megabytes per second. So we're not polling anymore. We're just saying subscribe to shard, and the shard will send us 2 megabytes per second. That means that if we have 20 consumers, overall we'll get 40 megabytes per second per shard. So we can start adding on consumer application, do the subscribe call again, and get another 2 megabytes per second. So before we had a 2 megabytes per second limit per shard, but now we get 2 megabytes per second per limit per shard per consumer. The reason is because Enhanced Fanout has Kinesis pushing data to consumers over HTTP2. And the added benefit of this is, first of all, we can scale a lot more consumer applications. And the other one is we get a reduced latency. So before, remember, we had this 200 milliseconds latency in case we had one consumer because it could pull 5 times a second. And actually, if you had more consumers, they all had 1 second latency. Well, with the Enhanced Fanout, now we get a reduced latency because data is pushed to us. And on average, you'll get 70 millisecond latency, which is a lot less than 200 millisecond or 1 second. So Enhanced Fanout is to me a game-changing feature, and I'm just happy to tell you that it exists. Obviously, you have to pay for it a bit more, and the pricing page on AWS will help you understand how much you have to pay for. Now, what's the difference between Enhanced Fanout and consumer standards, and when would you use each of those? So a standard consumer, you will use it when you have a low number of consuming applications, say 1, 2, or 3. And you can tolerate some latency. You can tolerate 200 milliseconds or more latency. And you want to minimize cost because this cost of standard consumer is included in Kinesis already. And you would use Enhanced Fanout consumers if you want to have multiple applications consuming the same stream. We're talking about like 5 or 10 applications at the same time. And you want very low latency requirements. So you can only maybe tolerate 70 millisecond latency requirements. And obviously, this will bring you a higher cost, as I said. See the Kinesis pricing page for that. And by default, though, when you use Fanout consumer, you have a limit of 5 consumers that can use Fanout, but you can increase that doing a service request on AWS support. So I hope that makes sense. I hope you're excited about this new feature. Honestly, it's awesome, and I'm pretty sure the exam will ask you about it very, very soon. So it's good to learn about it. To me, it's game changing because now we can have 20 consumers on a shard and not have any impact to each of them, which to me is really, really game changing. All right, I've said it enough. I will see you in the next lecture. From an exam and real world perspective, it's really important to understand how you can scale kinesis. So the first operation you can do is to add shards. And adding shard in kinesis world is called shard splitting, and we'll see why in a second. It can be used to basically increase the stream capacity. So remember how you get 1 megabyte per second per data of data per shard. Then if you have 10 shards, you have 10 megabytes, right? So if you want to increase the stream capacity, you need to split a shard. It can also be helped to use and divide a hot shard. So if you have a hot shard, one shard that's being used more than others, we'll just split it and it will probably increase our throughputs. So what happens when you split a shard? Well, the all shard is closed and will be deleted once the data in it is expired. So let's have a look with the diagram because I think it'll make a lot more sense. So we have shard 1, 2, and 3 in this example, and they occupy the same space. Now shard 2 is very hot, and we want to split it to increase throughput on the key space of shard 2. So we're going to do a split operation, and what's going to happen is that there's going to be shard 4 that's being created and shard 5 that are being created, and as you can see, they're occupying the same space as shard 2, but now because we have 2 shards, we have 2 megabytes per second on this space instead of 1 megabyte per second. Then the other shard 1 and 3, they remain the same. So before our shard looks like this, it has 3 shards, our stream looks like this, it has 3 shards, and then after the split, we have 4 shards, and we can see that 4 and 5 are occupying the space of shard 2. So shard 2 will be available as long as the data in it is not expired, but when it's expired, it will be gone. So now this is the state of our new kinesis stream. When producers write data to it, they have 4 shards to write to. So this is really important concept to understand because basically you can split as many shards as you want over time and increase your throughput this way. Now what's the inverse operation to adding or splitting shard? Well, is to decrease shard or merging shards. And so when you merge shards, you would use that to decrease the stream capacity and save on some cost. And it can be used, for example, to group 2 shards that have low traffic and you want to merge them together in order to save cost. So the all shards will be closed and deleted again based on data expiration. So now, for example, say we have this shard and it has our stream and has 1, 4, and 5, 3, just like before. And we want to merge 1 and 4 together. So we're going to merge them together and it's becoming shard 6. That's because maybe shard 1 and 4 didn't get much traffic, so we can merge them together and save some cost. So we merge them together and then shard 5 and 3, well, they remain on the same as before. And so now we went from 4 shards to 3 shards in our new stream because we've merged it. So you can see now how we can merge and split and merge and split, and we can basically modularize our entire kinesis data stream to increase and decrease throughput over time. This is how it works. A common scenario question in the exam will be asking you about a case where the producer is sending data to a kinesis data stream with the correct partition key, yet your consumer received the data out of order at some point. And so a reason for that would be resharding. So let's explore this use case. So when you do a kinesis resharding, you can read straight from the child shards after the resharding. However, if you haven't read all the data yet from the parent shard, then what's going to happen is that you may read the data out of order for a particular hash key. So let's look at it in the diagram. So we have the parent shard, and we have a device producing to kinesis data stream using the KPL, for example. And we have a consumer application running on EC2 using the SDK. So we're going to do get records API calls. So say that the IoT device, just before a resharding operation, sends some data 1 and 2. So in terms of consumption rate, our consumer application has been consuming everything in the parent shard up to the 2 data points, 1 and 2. Then we start a shard splitting operation. So from this parent shard, we're going to have 2 new child shards. And what's going to happen is that once the split is over, well, the IoT device is going to start producing to the new children shard because the parent shard will be closed for writes. So that means that the data points 3 and 4 are going to end up on the child shard. Now, if your consumer application isn't very, very smart, what's going to happen is that you can request data directly from the child shard.
before you have read the end of the parent. So that means that you will see data points 3 and 4 first, and then maybe 1 and 2 next. So this is something that can create out of order records, after a resharding operation. So the guideline is that after a reshard in your consumer application logic, you need to make sure that you have the logic to read entirely from the parent until there are no new records from the parent. That means you reach the end of the parent shard, and then you can start reading from the child shard. And this will guarantee the order of the records. Now, this can be complicated to implement. So as a note, the Kinesis client library, the KCL, already has this logic built in, even after the resharding operation, so you're good to go. But hopefully you're good with that use case, and this can come up in the exam.
So what about autoscaling? You may say, do we have to do these things manually? Well, there is autoscaling, but it's not a native feature of Kinesis. And there's an API call that you can use to update the shard count called update shard count. And you can implement some kind of autoscaling using AWS Lambda. There's a whole blog on it if you're curious. This is the architecture diagram directly from that blog. So read that blog if you're interested in implementing autoscaling, but you have to do it a bit manually to make it work. So what about Kinesis scaling? What are the limitations of it? Well, you cannot do resharding in parallel, so you need to plan capacity in advance. So that means you can't reshard 1,000 streams at a time, 1,000 shards at a time. That would not work. So this is why you need to plan capacity well in advance in case you're expecting some big throughputs. And you can only perform one resharding operation at a time. It takes a few seconds. So for example, if you have 1,000 shards, it will take you about 30,000 seconds or 8.3 hours to double the number of shards up to 2,000. So that gives you an idea that scaling in Kinesis is not instantaneous. It takes time. And as you can see, doubling from 1,000 shards to 2,000 shards takes over 8 hours. So you need to plan a lot in advance. On top of it, there are some limitations. Now, they're a bit complex and you don't need to remember them, but I've added in the slides just in case you need to use Kinesis in the real world and you need to know about them. So here they all are. Basically, that means that you can't scale up too quickly and you can't scale down too quickly. There is some limits that AWS imposes on you. So I won't read them out to you. You don't need to know them for the exam. Okay, just need to know that resharding cannot be done in parallel, and you need to basically resharding takes a few seconds for each shard. So remember that for 1,000 shards, it takes about 8.3 hours to double the number of shards to 2,000. That's what I want you to remember out of it. Don't need to remember all the limitations, obviously, but they're here just in reference in case you need them for your real world application. All right, so that's it for Kinesis scaling. I hope you liked it, and I will see you in the next lecture.
Now let's talk about how you can handle duplicate records in Kinesis data streams. And there are two cases when that can happen. There is on the producer side and also on the consumer side. So producer retries can create duplicates due to mainly network timeouts. And this is an exam question. So how does that work? Well, you have your producers. It could be applications. It could be using the SDK or the KPL. And they're producing into a Kinesis data stream. Now, when we do a put record and we send some data, then we know what happens. The data gets written into the Kinesis data stream. The data gets a unique sequence number, and then Kinesis data stream says, I've written your data correctly. But in case of a network timeout, then this acknowledgement may never reach our producer application, maybe due to a network timeout. And our producer cannot know that, so maybe it says, okay, I don't think this record has been written because I haven't received any acknowledgement back, and now there's a timeout. So what's going to happen is that the producer record is going to be retried by our application by reissuing an API call. So we're going to do a put record again for the same data, which is going to be written a second time into my data stream. And as you can see, the sequence number has increased from 123 to 124. And now the acknowledgement reaches back to our producer and we are good to go. But what happened is that from a Kinesis data stream perspective, we have created duplicate records because the same data was written twice and it got two different sequence ID. So although the two records have identical data, they also have unique sequence numbers, and so there will be two data points in our Kinesis data stream. So the fix for it is to embed a unique record ID in the data to be able to deduplicate based on that unique record ID on the consumer side. So this, although it looks scary, I would say rarely happens, but still is a case for you to know about and something the exam will test you on. Now let's talk about what can happen on the consumer side for duplicates. So the consumer retries can make your application read the same data twice. And the consumer retries can happen in 4 different type of use cases, but they all correspond to when your record processor will restart. So it could be when a worker terminates unexpectedly. It could be when a worker instances are added or removed. It could be when shards are merged or split, or when the application is deployed. So remember these 4 cases because they can come up as well in the exam. So the fix for that is quite difficult, and the documentation is pretty vague about it. But the idea is that you make your consumer application idempotent. That means that if you read the same data twice, then it does not have twice the same side effects. And the other recommendation provided by the documentation in AWS is that if somehow your final destination can handle duplicates, it's recommended to do it there. For example, if you can rely on that unique record ID and you insert that into a database, then the database will not allow you to insert that unique record ID twice. And so that could be a good one for you. If you want more information, you can read the documentation here. But from an exam perspective, you need to know that network timeouts can introduce producer-side duplicates, and that these 4 consumer retries can introduce duplicates from a consumer perspective because the data is going to be read twice. So that's it for this lecture. I hope you liked it, and I will see you in the next lecture.
Okay, let's talk about Kinesis security. So security is going to be a big part in your exam. It's a dedicated section to it. And so we need to know about security for each technology. So let's talk about Kinesis. Basically, we control access and authorizations to Kinesis using IAM policies. And we can get encryption in flight using the HTTPS endpoints. That means that the data we send to Kinesis will be encrypted and it cannot be intercepted. We can also get encryption at rest within the Kinesis streams using KMS. And if you wanted to encrypt your message client-side and decrypt it client-side, then you must do this manually. So it is possible to do, but it is harder. There are no clients to help you do that, and it's up to you to implement that kind of technology, encryption technology. Finally, if you wanted to access Kinesis within your VPC, within a private network, you could use something called VPC endpoints. They're accessible for Kinesis that basically allow you to access Kinesis not on the public internet, but on your private VPC internet. So that's it for Kinesis security. Don't worry, overall, at the end of the course, I'll have a whole section on security describing in depth the security for each technology, but at least it gives you some kind of idea of how Kinesis security works. All right, that's it. I will see you in the next lecture.
Okay, so we've seen Kinesis data streams, now Firehose. So Firehose is actually quite easy. It is to store data into target destinations. So we have producers, and it could be, again, a bunch of applications from before that can send directly the data into Kinesis data Firehose, or Kinesis data Firehose can read from your Kinesis data stream from Amazon CloudWatch or AWS IoT. But the most common you're going to see is going to be Firehose reading from Kinesis data streams. So it's going to read the records one by one, up to 1 megabyte at a time, okay? And then if you want to transform the record, we could have a Lambda function created to transform the record, to do some small modification. And then Kinesis Data Firehose will try to fill a big batch of data to write that data into a target database or a target destination, okay? So that's why it's called batch writes. It doesn't write stuff instantaneously. It will try to batch them to write them efficiently. So therefore, Kinesis Data Firehose is a near real-time service. So in terms of destinations, we have AWS. So Amazon S3 is very important. Amazon Redshift, and to write to Redshift, Kinesis Data Host will first write into Amazon S3 and then issue a copy command into Redshift, or Amazon Elasticsearch. And you have to remember these 3 destinations. They're very important. Other destinations include third-party destinations from partners, such as Datadog, Splunk, New Relic, and MongoDB, but there could be others coming up in the future. You don't need to know them, so this is why I will not update this slide if there are new partners, but you can see that there will be new partners over time. Or also, there could be a custom destination. As long as there is a valid HTTP endpoint as an API, you can have Firehose deliver data into that destination. And finally, if you have failure for processing or you want to archive all data going to Firehose, it is very much possible to send all or just a failed data into a backup S3 bucket from Kinesis Data Firehose.
While Kinesis Data Firehose is a fully managed service, does not require any administration, and it's near real-time. So you have to remember this. While Kinesis Data Streams is real-time, Kinesis Data Firehose is called near real-time. The reason is, and we'll see this when we see the batching, there's a 60 seconds latency minimum if your batch is non-full. So we don't have the guarantee that data will be right away in the destination, and there is a near real-time thing with Kinesis Data Firehose. So what do you use Firehose for? Well, you're going to load data into Redshift, Amazon S3, Elasticsearch, or Splunk. You have to remember these 4 destinations by heart. So remember Redshift, S3, Elasticsearch, and Splunk. The really cool thing about Kinesis Data Firehose is that unlike Kinesis Data Streams, there is automatic scaling. That means that if you need more throughput, Kinesis Data Firehose will scale for you, and if you need less, it will scale down for you as well. It also supports many data formats and also is able to do data conversion, for example, from JSON to Parquet or RC if you use S3. The other data transformations you can do are done through AWS Lambda. For example, if you wanted to transform a CSV into a JSON file, we could use AWS Lambda to do that transformation coupled with Kinesis Data Firehose. Also supports compression when the target is Amazon S3, so you're able to compress that data being sent into gzip, zip, or snappy directly into S3. And if you load it into Redshift further down the road, then gzip is going to be the only supported compression mechanism. Finally, you're going to pay only for the amount of data that goes through Firehose. And so the really cool thing is that if you don't need to provision Firehose in advance and you don't get billed for provision capacity, you just get billed for used capacity. Finally, an exam will trick you into thinking that Spark or the KCL can read from KDF or Kinesis Data Firehose. This is not the case. Spark streaming and Kinesis client library do not read from Firehose. They only read from Kinesis data stream. So I just wanted to make that very, very clear right now. Okay, so what does the delivery diagram look like? Well, we have Firehose in the middle, and it's going to have a source. For example, my source in this example is a Kinesis data streams. So it's going to send that stream into Firehose, and maybe we'll be able to do some data transformation. So remember I said CSV to JSON. Actually, there's a bunch of blueprints available for AWS Lambda to help you transform the data in Firehose in the format you want. Once the data is formatted and transformed, we can send the output, for example, to an Amazon S3 bucket if S3 is your destination, or if Redshift is your destination, actually it goes through S3 and then there will be a copy command issued to put that data into Redshift. So what about the source records? Can we get the source records into an S3 bucket? The answer is yes. Any source record that goes through Kinesis Data Firehose can be configured to land into another bucket of your choice. So if the exam asks you, okay, how do we get all the source data into a Amazon S3 bucket through Kinesis Data Firehose? Well, this is directly a feature from Firehose. There's also a really good feature. In case there is a transformation failure, we can archive that transformation failure into an Amazon S3 bucket, or even if there is a delivery failure, well, we can also have that delivery failure put into an Amazon S3 bucket. What you remember out of this diagram, is that you don't lose data with Kinesis Data Firehose. Either it ends in your targets, or you will have a recollection of all the transformation failures, the delivery failures, and even the source records if you wanted to, into another S3 bucket. So remember this diagram, it's really important. That's basically your understanding of Kinesis Data Firehose. Now we're going to look into how often Kinesis Data Firehose sends the output data to the target. And for this, we need to understand the Firehose buffer sizing. So how does Firehose work? Well, Firehose will receive a bunch of records from the source, and it will accumulate all these records into a buffer. And that buffer, hence its name, is not flushed all the time. It's flushed based on some rules. It's based on time and size rules. So we need to define a buffer size. For example, 32 megabytes. That means that if you have enough data from the source that reach and fill a buffer size of 32 megabytes, then automatically it's going to be flushed. The other setting is buffer time. For example, 2 minutes. That means that if after 2 minutes your buffer size is not full, nonetheless it's going to be flushed. So Firehose can automatically increase the buffer size to increase throughputs. So it scales really nicely for you and accommodates any throughput size. So if we have high throughput, we have a lot of data going through Kinesis Firehose, then the buffer size limit will be hit and will flush based on buffer size. But if we have low throughputs, usually that means that the buffer size limit will not be hit, but instead the buffer time limit will be hit. Now, buffer time, the minimum you can set is 1 minute. And buffer size, you can set a few megabytes. Okay, so Kinesis data streams versus Firehose. They look similar, but they're actually not. Streams is you're going to have to write custom code for your producer and your consumer. And it's going to be real time. We're going to get 200 millisecond latency for classic consumers or 70 millisecond latency for enhanced fan-out consumers. And you must manage scaling yourself. So you need to perform shard splitting and shard merging to have your cost and your throughput move over time.
You get data storage between 1 to 365 days, replay capability, and multiple consumers.
You can also use this with Lambda to insert data in real time into Elasticsearch, for example. Firehose, on the other hand, is going to be fully managed, auto-scaling. It will send data to S3, Splunk, Redshift, and Elasticsearch for you. And it has some serverless data transformation it can do with AWS Lambda. And it's near real time. The lowest buffer time, as I said, is 1 minute. It's automated scaling, and there is no data storage. So Firehose does not replay data or stuff like this. So you need to really see the differences between the two. To me, they're clear around what they are, but you have to remember. Finally, remember that with the producer or the KPL, you can produce either into Streams or Firehose. That is fine. So remember about your use case. If your use case is to have applications read data, maybe it's going to be Streams. But if all your use case is about is to send data into S3 or Redshift or Splunk, then maybe Firehose is going to be the use case for you. And remember the real-time versus near real-time constraints. So that's it for Firehose. I hope you liked it, and I will see you in the next lecture.
In this lecture, we're going to talk about the integration between CloudWatch logs and Kinesis. So CloudWatch logs are real-time streaming of logs, and you can stream them actually into 3 destinations. And this is something the exam will test you on. So you can stream your CloudWatch logs into either Kinesis data streams or Kinesis data Firehose or a Lambda function. And we're going to see these 3 use cases as architectures in this lecture. So the idea is that using what's called a CloudWatch logs subscription filter, then you will be able to link your CloudWatch logs to these 3 destinations. And to do so, right now, it's mainly possible using the AWS CLI. Okay, so how does that work? So let's say we want to have our CloudWatch logs directly flow into Amazon Elasticsearch in near real time. So what sort of architecture would you do? Well, you have the CloudWatch logs, and it flows into your subscription filter. And then you link it to Kinesis Data Firehose because we have a near real-time requirement. And we know that Kinesis Data Firehose can send data in real time into Amazon Elasticsearch, but also other destinations, for example, Redshift or Amazon S3. But the cool thing is that because we're using Kinesis Data Firehose, well, we can also integrate it with a Lambda function to do transformations. And that Lambda function, for example, can do any kinds of data cleaning or enrichment you may want. So it's quite a flexible type of architecture. Okay, now let's say we want to, instead of near real time, do real-time load into Amazon Elasticsearch. So in that case, same destination, but different purpose. So different means of achieving it. So we have our subscription filter still. But this time, we are going to load this directly into a Lambda function, which is going to stream all the records. And that Lambda function can use API calls to load data in real time into Amazon Elasticsearch. So we've removed Kinesis Data Firehose because it was near real time. And instead, we've replaced it with a Lambda function. Now, what if you want to do real-time analytics on these logs? Well, in that case, we have the CloudWatch logs and subscription filter. But this time we will stream it into a Kinesis data streams. Well, why? Because now we can use Kinesis data analytics to do some real-time analytics onto our Kinesis data stream. And maybe the outcome of Kinesis data analytics can be streamed into a Lambda function, and that Lambda function can do any kind of things you want, for example, alerting based on the outcome of your real-time analytics, and so on. But in this lecture, what we've shown is that CloudWatch log subscriptions can go into 3 different destinations, so Firehose, data streams, and Lambda functions, and they all serve different kind of purposes and use cases. And this is something the exam will test you on. Well, that's it. I hope you liked it, and I will see you in the next lecture.
Let's begin by building out the core of much of the systems we're going to build throughout this course. We're going to set up a Kinesis Data Firehose stream to capture data from a server log being generated on an Amazon EC2 instance and publish that into a data lake housed in Amazon S3. Later in the course, we'll use that S3 data lake in many different ways. As you can see, we'll analyze it using a multitude of other tools, but the first step is to create it. So let's dive in and get started. So I'm signed into my AWS Management Console here, and if you don't already have an Amazon Web Services account, go ahead and take care of that right now. But once you're logged in, we're just going to search for the Kinesis service. So up top here, I'm going to type in Kinesis and select Kinesis. And for this activity, we're going to be creating a data fire hose as opposed to a data stream. So let's click on Create Delivery Stream. And we need to tell it where that data is coming from and where it's going. So from source, let's go ahead and select Direct Put, because we're going to be actually putting data directly into this fire hose stream using the Kinesis API on our individual EC2 instances to put data into it. The destination is going to Amazon S3, as we saw in our diagram. And we need to give our delivery stream a name. How about purchase logs? Moving on, we do not need to transform our data as it goes, but we'll revisit that later on. It's a useful capability if you need to transfer things into a different record format, for example, into JSON. If we're putting it somewhere else, it might require that, but we'll skip that for now. We need to tell it where to put this data into S3. So let's go ahead and create a S3 bucket for it. We need to give it a unique name. So you're going to have to come up with your own name that's different from mine, that's different from everybody else's for that matter, and remember what it is. So for me, I'm just going to call it orderlogs-sundog.edu. You might want to just say dash whatever domain you might own instead, but it has to be a unique name. Do not enter what I just typed in here. Make something up that's unique. My region of US East 1 is appropriate for where I live, so I'm going to keep that as the default for me. And that's all we really need. I don't really need any special security going on here. I will retain the default setting to block all public access to this bucket because I'm just going to be viewing it from within my account. I don't need to get at it externally, so I'm not going to worry about that. I do not need bucket versioning for this application. I'm just playing around. I don't need a backup copy, don't need any tags, nor do I need encryption on the server side because I'm not dealing with any sensitive data here. It's all just sample data. But obviously in the real world, you'd want to think about these things, right? Go ahead and create bucket. And it looks like my name is not unique after all. Somebody took it. So how about education? Let's try that instead. All right, now we're good. All right, back to the Kinesis page here. Let's go ahead and select that bucket we just made. I have a lot of them. Let's see. There it is, orderlogs-sundog education. The defaults here should work well for me. I do not need any special dynamic partitioning, although it has that capability if you need it. I do not need a special prefix on my bucket or the error output, but I am going to take a look at the buffer hints and compression and encryption settings here. The 5 megabyte buffer size is fine. That's the chunks of data that it will deliver at once, but I'm impatient. I don't want to wait 5 minutes for my data to come through, so I'm going to go ahead and set that to the minimum of 60 seconds for the buffer interval for sending my data across to S3. Important thing to remember there, the minimum for that is 60 seconds and the maximum is 900 seconds. They recommend 5 minutes of 300 seconds, but this is relevant to the certification exam because the minimum is 60 seconds, right? So if you see a question that says, I want to send data across every second, Firehose is not going to be able to do that. 60 seconds is as fast as it will go. So that's a very important limitation to remember. I'm going to go ahead and stick with the defaults for compression and encryption. Again, you could mess with that if you wanted to. If you wanted to compress the data before it goes into S3 to save some storage costs, you can do that. And if you want to encrypt that using a KMS master key, you can do that as well. But for our little example here, we don't need that. Let's go ahead and click Create Delivery Stream. And we'll just wait for that to be created and we can start playing with it. So now that we have our Firehose delivery stream set up, we need to set up an EC2 instance that we're going to use to actually feed data into that stream, where we'll ultimately end up in our S3 bucket. So I'm back at the AWS Management Console here, and we're going to click on EC2, however you want to get there. And we're going to launch a new instance that we're going to play with here. So just hit Launch Instance and Launch Instance again. And we're going to choose the Amazon Linux 2 AMI, whatever the latest version of that is. Don't get too hung up if that specific number changes, because it changes a lot. Click on Select. And we'll stick with the T2 Micro free tier version here. If you do have a new enough account, this won't cost you a penny, which is awesome. We're going to click on Review and Launch. There is a security warning there that you'd want to pay attention to in the real world, but just for this course, we're not going to have this up too long. Let's go ahead and click Launch again. And there is some security that we'll have in place, so we need to have a key pair, an actual private key to log into this thing, so that's enough for us for now. You'll need to create one, though, if you don't have one already. So we can say create a new key pair, give it a name, I don't know, big data, how about that? And we'll hit download key pair. And be sure to keep that file around because you're going to need it to connect to that instance. Once we're done, we'll say launch instances. And now we just wait for that to spin up. So let's go click on View Instances. And if we give it a minute or two, that should change from pending status to running status. So I'm just going to come back when that's ready. Okay, that was pretty quick. So we're running already. That was about a minute, pretty quick. So what we can do now is click on that and click on the Connect button. And that will guide us to how to connect on it. Now, one thing that's kind of new is this new EC2 Instance Connect thing. You could actually just click on that and click the Connect button, and it would give you a browser terminal window or terminal window right within your browser here that you can use to connect to it. So if you want to cheat and kind of do things the easy way, just hit Connect there and you'll be done. But, in the real world, you'll probably want to connect to it from some sort of an SSH client. And for guidance on that, you'll click on the SSH client tab and it will tell you what to do. So on Mac or Linux, this is pretty much what you do. You're just going to download that bigdata.pem file that we downloaded earlier, do a changemod command on there to make sure that you can access it, and then just say ssh-i, path to that PEM file, and that particular address to actually log in. Now on Windows, it's going to be a little bit more involved. So on Windows, we're going to have to download the PuTTY application first and configure that. So let me walk you through how that works. If you need to get PuTTY, just search for it, PuTTY Windows, and it should lead you here eventually, ssh.com/ssh/putty/download. And from there, you can actually download the package for Windows. You want 64-bit most likely. So go ahead and install that if you haven't already. First thing we need to do is convert our PEM file to a PPK file that PuTTY can use for SSH. So to do that, I need to launch the PuTTY-gen utility that ships with PuTTY. If I go down to PuTTY here in my Start menu, select PuTTY-gen, and hit Load, and select that PEM file that I just downloaded. To do that, I need to change the filter to all files so I can actually see it. And there's bigdata.pem. Open that, OK, and hit Save Private Key, and that will convert it to its PPK format. We'll call that big data as well. So now I have a bigdata.ppk file that will make PuTTY happy. Let's close out of PuTTY-gen and open up the PuTTY application itself. Now I'm going to paste in the host name that EC2 gave me. Just copy that from this Connect window here. Go ahead and paste that into the host name. And we need to go into the SSH area here. Open that up, click on Auth, and select the PPK file that we just made. And go back to the main session window here. We probably want to save this so we can get back to it easily. We'll call it AWS Big Data. And hit Open. And we should be able to connect. Hit Yes. And we want to log in as EC2-user. And in we are. Cool. So the first thing we need to do is install the Kinesis client application here so we can actually send this log data into Kinesis Firehose. To do that, we're just going to type in sudo yum install -y aws-kinesis-agent. And make sure you spell everything right. It's easy to spell Kinesis wrong. Off it goes. And we have Kinesis agent installed. Cool. So now we need to get our fake log data that we're going to be playing with throughout the course. Let's go ahead and download that from our server here. We can just type in wget http://media.sundog-soft.com /AWS big data. Pay attention to capitalization here, folks, because it does matter. /log generator.zip. All right, now double check you typed everything correctly there. One little typo and it won't work. All right, we have our log generator.zip file. Let's go ahead and unzip that. Unzip log generator.zip. And you can see that we have both a Python script that I wrote that will actually generate fake log data into the var log directory of our instance here, and also the source log data here, onlineretail.csv. Let's go ahead and change the permissions on that script so we can actually run it. Change mod a plus x log generator.py. And let's take a quick look at what we have here. If you want to examine that script, you can. You don't really need to concern yourself with how it works, but what it does is it actually reads however many lines you want from the onlineretail.csv file and basically creates a bunch of CSV files inside the var log cadabra directory for you. And if you want to take a peek at that log data itself, we can do that as well. You can see that's in the onlineretail.csv file. And it contains, as it says, an invoice number, a stock code, a description, a quantity, invoice date, unit price, customer ID, and country for every order. This is a real e-commerce data set, and it is from some UK retailer that sells, crafty goods, basically. So real data here, and it comes with real-world problems, too, as you'll see later on in the course. Hit Q to get out of less there. All right, so let's go ahead and create our log directory that we're going to put everything in. Let's say sudo make dir /var/log/cadabra. And again, make sure you spell that right. It's very easy to misspell cadabra because it's not a real word anyway. And let's go ahead and configure Kinesis to write our stuff into there. So let's say cd/etc/aws-kinesis. And in here is the actual configuration file for the Kinesis agent. So we can say sudo nano, that's our editor, agent.json. And this is the configuration file for the Kinesis agent. So let's go ahead and reshape this configuration file to be what we need. First thing we need to do is set up the endpoint for Firehose. These first two lines are okay to keep as is. But if you're not in the US East 1 region, you'll need to specify explicitly where the endpoint for Firehose is, because it does default to US East 1. If you're somewhere else, just head back to your AWS console here and go back to Kinesis. And you'll see here the purchase log stream that you created earlier. And on this page, you should see the delivery stream ARN. And in there, you should see the region name that has been created within. So for me, that's US-East-1. If that's the same for you, then you don't need to do anything. But if it is different, you'll need to go back to this setting here and type in the following: Firehose dot whatever your region is. For me, that's US-East-1 dot Amazon AWS.com, just like that. All right, the next thing we need to deal with is managing permissions. We need to make sure that our Kinesis agent can talk to our delivery stream. By default, it cannot. So there's a few ways of doing this, and you'll see me do this in a couple of different ways throughout the course. One is to explicitly copy in a set of access keys here. So you can actually put in a public and secret access key here within the configuration file. To do that, you would want to go back to your AWS console and go to IAM and create a new user. Don't follow along with me here, though, because I'm not actually going to end up doing it this way. Just kind of illustrating another way of doing it. I could go to the users, create a new user, and then copy the access key and secret access key for that out somewhere. And with that, I could put in some settings here for AWS access key ID. Again, do not type this because I'm just illustrating. And then within quote, you would have your access key ID, comma, and then we'd have another line called AWS secret access key, to whatever the secret access key is as well. Now, that is one way of doing it, and it will work if you do it that way. However, that's not really considered best security practice, because if someone were to break into the CC2 node and got this configuration file, they could potentially have the keys to get into your account with administrator access. That would be bad. But if you see those lines in some configuration files later on in the course, that's where they came from. Let me show you a better way of doing it. So let's go back to our AWS console here and go back to EC2. All right, so let's head back to the EC2 console here and make sure that our instance has all the permissions it needs to talk to our Firehose stream. So we'll go back to the instances view here, and select whatever you called your instance here. And we're going to go up to the Actions menu, and under Security, go to Modify IAM Role. And now we'll create a new IAM role. And we'll create a new role. We're going to select EC2 as the use case and go on to the permissions screen. And we're just going to select Administrator Access to keep it simple. Now, you could be more secure and specifically only grant access to this instance of the specific services that it needs, but we are going to be using this instance further on in the course, so we're going to keep it simple and just let it access all services on our behalf. And we'll move on to the tags. Skip that, go to the review screen. Give this thing a name, whatever you want to call it, EC2 admin, whatever makes sense to you. Review that the administrator access policy is attached to it and hit create role. All right, now back to our EC2 screen. Let's go ahead and refresh this and choose the role that we just made and hit save. And let's turn our attention back to the terminal. So we're going to turn our attention to the flows section here. And this first section is for a Kinesis stream and not a Firehose stream. So we're just going to go ahead and delete that whole section. So I'm going to go to that first curly bracket there and hit Control K repeatedly to get rid of that entire section. And now we're left with this couple of lines here. So we're just going to change this to match our Firehose stream data. First of all, we need to tell it where to find the log data that we're trying to put into it. So I'm going to delete the existing file pattern there and replace it with /var/log/cadabra. Make sure you spell that right. /star.log. And we'll change the delivery stream to the name of our Firehose stream, which is purchase logs. All right. So it should look more or less like this. Double check things. Make sure you don't have any typos. Make sure you're not missing any commas. Make sure your capitalization is right. Make sure you spelled Cadabra right. If everything looks okay, hit Control O to write that out. Hit Enter. And Control X to get out of the editor. So everything is now configured properly to actually monitor our var log Cadabra folder, and any new data that the Kinesis agent finds is going to shove into Kinesis Firehose, which in turn will shove it into S3 for us. All we need to do now is start the Kinesis agent. So to do that, let's type in sudo service aws-kinesis-agent start. And that time it worked. Cool. Now we also want to make sure that it starts up automatically when we start our instance here. So to do that, we're going to say sudo check config, just like that. Make sure you pay attention to spelling. aws-kinesis-agent on. All right, now let's go back to our home directory, cd tilde, and we can actually kick this thing off. So let's type in sudo./loggenerator.py. And we'll pass in an argument of 500,000. That means that we are going to generate 500,000 orders in our log directory and see if Firehose successfully puts it into S3. Let's go ahead and kick that off. It's a lot of data, so we'll take a moment. All right, looks like it worked. We can go check that out. Go to var logs log Cadabra. And sure enough, there is a giant log full of 500,000 orders. So let's take a look at what Kinesis is doing. To monitor its progress, we can just type in tail-var/log/aws-kinesis-agent/aws-kinesis-agent.log, just like that. And here we can see what the agent is actually doing. You can see that it looks good so far. It looks like it has actually started to parse some of these records already. Taylor has parsed 237,000 records, transformed 0, blah, blah, blah. Here we see that it's actually already sent 142,000 records successfully to the Firehose destination. And we're just going to let that sit there until it's actually done. It'll take about 5 minutes for it to actually get through all that data. So just keep an eye on this until it actually says that 500,000 records have actually been sent successfully. I'll pause and come back when that's done. All right, a few minutes have passed and it looks like it did catch up. We can see here in the log that it has processed 500,000 records and sent them successfully to the destination. So yay. Control C to get out of that. And let's see if that data actually is in S3. Let's go back to our AWS console. Select S3. And you can see we have our order log sundog edu bucket. And you can see it did some interesting stuff here. It actually broke it up by date here for us automatically. So that is today's date and today's hour. And here you can see that it did in fact split that data up into 5 megabyte chunks. If you recall, we actually set the policy for this Kinesis Firehose stream to save data either every 60 seconds or every 5 megabytes, whichever comes first. And in this case, it was every 5 megabytes. So cool. We actually have separate log data here for each 5 megabyte chunk of data. And we can go ahead and open one up and see what it looks like. Let's hit open. With some text editor of your choice. And sure enough, there is some of our data here. So you can see that we have successfully published data through Firehose from an EC2 instance, from monitoring a log directory on our instance there, into Amazon S3, where it's broken up into CSV data that can later be analyzed by other systems in the AWS ecosystem. So cool. Some of the groundwork there that we're going to need for the rest of the course, but it's there and in place and working now. So we now have an S3 data lake of order data just sitting there waiting for us to play with. So woohoo. Let's move on and learn some more things that we can do with that stuff. So to illustrate the use of Kinesis data streams, we're going to start building out that order history app that we talked about earlier on. Now remember, what we're trying to do is build mobile app access to a user being able to access a history of their orders on Cadabra.com. And at a whole, this system looks like this. We're going to publish server logs from EC2, which we've already set up earlier. And now instead of Firehose, we're going to publish that into Kinesis data stream so that this data is accessible really in real time. Later on, we'll connect that to AWS Lambda and DynamoDB, but for now, we're just going to focus on this piece of it, actually connecting our EC2 instances through the Kinesis agent to a Kinesis data stream instead of Kinesis Firehose. And we'll see that's pretty easy to do. So from our AWS management console, I've already logged in here. Let's go to Kinesis. Should either be in your list of services here or just search for it in the search box, whatever works for you. And we are going to create a new data stream as opposed to a data firehose. So this is going to be a stream that's sitting around waiting for data all the time, and it will deliver it in real time. And we need to give our data stream a name. Let's call it Cadabra Orders. Pay attention to spelling and capitalization, it all matters. And we need to decide how much capacity we need. For our little toy example here for playing around, we don't need much. We're going to just stick with the on-demand mode here. This is a new feature in Kinesis in 2021. And it allows you to pay by usage as opposed to paying by the hour, which is really good, especially for what we're doing, because we're just going to be using this for a few minutes at a time. So with on-demand capacity, you can see that we're just paying by the throughput as opposed to provisioning dedicated capacity that's sitting there all the time waiting for us. So if you have a real-time application in production that has sort of a steady stream of traffic, provision might make sense for you. But for just testing and development or things that are really bursty in nature, on-demand will be the right choice. Now the exam loves to talk about the capacity limits of these various modes. So let's review that real quickly here. We can see that an on-demand data stream gives you up to 200 megabytes per second and up to 200,000 records per second for write capacity. And if you go beyond that, your stream will throttle. On the read side, we get 400 megabytes per second, and that is for up to 2 default consumers. You can use enhanced fan out. If you need more than that, that will give you up to 20 consumers, each with its own dedicated throughput. On the other hand, for provision capacity, you might see this on the exam as well. Each shard comes with 1 megabyte per second and 1,000 records per second for write capacity and 2 megabytes per second of read capacity. And if you go beyond that, your application will throttle, which you don't want. So for most applications, on-demand will be more than enough. So I'm just going to stick with that. It's certainly enough for us, and it will ensure that if we do forget to shut this data stream down when we're done, we're not going to keep getting billed for it forever, which will save you some money. This does cost real money, by the way, guys. So just so you know, just a few cents, not a big deal. But if you are uncomfortable with spending anything, you might just want to watch instead of following along. All right, we have some various settings here that we can look at on demand. Data retention of 1 day, yeah, that works for me. We're just messing around. Server-side encryption is initially disabled. That's fine. I'm not dealing with any sensitive data. And monitoring enhanced metrics is disabled. We don't need enhanced metrics for what we're doing. We just need to be able to see some basic stuff to confirm that it's working. And as you can see, this is all changeable after you make it anyway. So if you change your mind later on, you can do that. Let's hit Create Data Stream. And that'll take about 10 minutes to create. So while we're doing that, let's move over to EC2 and set things up there. Let's go back to our EC2 instance in PuTTY here for me. I'm already logged in. Go ahead and log in if you need to. And we'll go back to the cd/etc/aws-kinesis folder and edit our configuration file again, sudo nano agent.json. All right, so we just need to add in a new flow here to actually define our new Kinesis stream. And while we're at it, we're going to tell the client to actually convert our CSV data into JSON format so that our Lambda function can use it a little bit more easily. And it's kind of a neat feature of the agent that it can do that conversion for you. Now, to make life easier, I'm not going to make you type this all in. If you go to the course materials and go to the order history folder, you'll find the agent.nano.txt file here. And all you have to do is copy this flow out of it. So just select from this bracket to that bracket there and go ahead and copy it. And we're going to go underneath the flows section here and right click to actually paste that in. Follow it up with a comma and a return to make sure it lines up, and it should look like that. So basically we now have two different flows installed here. One, and we'll walk through this, is again looking at the var log Cadabra folder, just waiting for new logs to come in. It's going to feed it into the Kinesis stream, not delivery stream for Firehose, an actual stream in real time called Cadabra orders that we just created. It will partition it randomly to evenly distribute the processing of that data. And for data processing options, we're going to tell it to use the CSV to JSON converter that's built into the agent. And we also gave it a list of all the field names, so it actually knows what to call each field of data in the CSV as it converts it to JSON data. And again, that includes things like invoice numbers, stock codes, descriptions, quantities, so on and so forth. We close that off with a end bracket there and a comma. Don't forget the comma. It's so easy to forget that. And we should be in good shape at this point. Make sure your file looks like that. Control O to write it out. Enter and Control X. All right, we're ready to rock and roll. Let's see if this thing actually works. To pick up that new configuration, we're going to restart the agent. So to do that, we'll say sudo service aws-kinesis-agent restart. And it shut down okay, and it started back up okay. If you did get a failure there, go back and double check that configuration file because something's probably wrong. Let's see if this is actually working. Let's go back to our home directory, cd tilde, and put a few more logs in there. sudo./loggenerator.py. And by default, that will just write out 100 things. Write out 100 new lines. Let's go ahead and tail the log and see if it gets processed or not. tail-f/var/log/AWS Kinesis agent/AWS Kinesis agent log. And there you see it. Taylor has parsed 100 records, transformed 100, and successfully sent 0 so far. And after a couple of minutes, you can see that it actually updated, and it has now sent 200 records successfully to destinations. Wait, Frank, you might say, I thought we only put 100 records in there. Well, remember, we're actually sending them to two different places at once. We're sending them both to our Firehose stream that we set up earlier and to our real-time Kinesis stream as well that we just set up now. So it's actually processing every record twice there, sending every record to two different places. So according to the log, things are happy, and we actually have data going into our Kinesis stream. We can actually go back to our console. Let's Control-C out of this tail first. So we're back at the Cadabra orders stream page here that we just created, and navigate to that if you need to. Click on the monitoring tab so we can see what's going on with it. And you might have to hit the refresh button periodically to pick up new data. So if you don't see anything, just hit refresh. But let's scroll down and take a look. And you can see that we are actually seeing some data here in the CloudWatch metrics here. We actually successfully put some records here. And you can see the latency and the The counts that went in, 100, looks right to me. So sure enough, we do have data going into our Kinesis stream. Now we just have to do something with it, but we'll do that in our next hands-on exercise.
So SQS is a much smaller topic exam for the big data exam. Still, I just want to give you an overview, just a fresh refresher on SQS. Now, you don't need to remember all the details. Overall, we'll see the differences of SQS and Kinesis in the next lecture, but you just need to get an overall understanding of how SQS works. So let's have a look. SQS is a queue, and producers will send message to the SQS queue, and a consumer or consumers will pull messages from that queue. That's basically how a queue works. Now, that looks very similar to Kinesis, but it's actually very, very different. So SQS is AWS oldest offering, over 10 years old. It's fully managed, and it will scale automatically even if you have 1 message per second to 10,000 per second. There's no limit to how many messages per second you can send to SQS. The default retention period of a message is 4 days, but you can have a maximum of 14 days if you wanted to. There's no limit to how many messages can be in the queue, and it has extremely low latency, less than 10 milliseconds for each publish and receive API. There is horizontal scaling in terms of number of consumers, so you can scale as many consumers as you want, and you can have duplicate message at high throughput because you get at least once delivery occasionally. You can also have out-of-order messages, so it's not as good of an ordering as Kinesis, and there is best effort ordering being done. Finally, the messages have to be smaller than Kinesis. There's a limitation of 256 kilobytes per message sent, and you need to remember that limit. Now, how do we produce messages? Well, messages in Kinesis, they have a body, and as I said, they're up to 256 kilobytes, and they're made of a string, so made of text. And you can add metadata attributes to it. You can add key value pairs, basically, on top of that message. You can provide a delayed delivery, that's optional, and then that message is sent to SQS. What you get back from it is a message ID and an MD5 hash of the body, just to remember what you've sent to SQS. So it's very different from Kinesis. Kinesis, remember, was sending bytes. Here we're sending string. Kinesis was having 1 megabyte total max size. Here we have 256 kilobytes. Okay? Now, consuming messages, how does it look like? Well, consumers, they pull for SQS for messages, and they can receive up to 10 messages at a time. And they have to process the messages within what's called a visibility timeout. And then when they're done processing that message, they will delete that message from the queue using the message ID they received and the receipt handled. That means that basically, when you have SQS, your consumers will pull messages, and your consumers will process these messages and then delete them from the SQS queue. So the messages cannot be processed by multiple different consumer applications. That's a very big difference versus Kinesis. So remember that process. Consumers pull messages from SQS, process them, and then delete them. Now there is a new type of SQS queue. There was a standard queue before, and now there's the FIFO or FIFO queue. And that means first in, first out. It's not available in all regions, but I think it's almost there. And basically your name of the queue must end in .FIFO to indicate that it is a FIFO queue. And you get lower throughput now. You have limits. You get up to 3,000 messages per second with batching, or 300 per second without. So definitely lower throughput. But what you get is that the messages are processed in order by your consumers. So you get first in, first out type of ordering. Messages will be sent exactly once, and you have a deduplication interval of 5 minutes if you send something called a duplication ID. So it's different use case, obviously, less throughput, but more guarantees on the ordering if that's something you need. The FIFO queue works that if your messages are sent 1, 2, 3, 4, 5, then they will be also read in the order 1, 2, 3, 4, 5 by your consumers. So about that limit of 256 kilobytes, how do we send large messages in SQS? It's not really recommended, but there is something called the SQS extended client, which is a Java library, which uses a trick. Basically, it will use an Amazon S3 bucket as a companion, and will say, okay, I'm going to send the very large payload, maybe like 10 gigabytes or 5 megabytes to 10 megabytes to S3, and it will send a message metadata in the SQS queue. And then the extended client on the consumer side will receive the small metadata message saying where the file is in S3, and the consumer will be able to read the large message directly from S3. So this is how you circumvent the 256 kilobytes message size limit if you wanted to using the SQS extended client, which can be really helpful for big data. Now, use cases for SQS will be for decoupling applications. For example, if you want to handle payments asynchronously, or buffer writes to your database. For example, if you have a voting application and you expect a peak in throughput and you need to be able to scale very quickly, or handle large loads of messages coming in. For example, if you have an email sender. SQS can also be integrated with autoscaling through CloudWatch if you had EC2 instances reading from your SQS queue. Now, what about limits? Well, you have a maximum of 120,000 in-flight messages processed by consumers at a time. The batch request can only pull up to 10 messages of 256 kilobytes maximum. The message content is text, so it has to be XML, JSON, or just text itself. And the standard queue themselves, though, they have unbounded, unlimited transactions per second. So you can have as many messages per second in terms of throughput going into SQS. The FIFO queue, though, they support up to 3,000 messages per second using batching, so remember that. And the max message size is, I think, 10th time I say it, is 256 kilobytes. If you need more, you use the extended clients. The data retention period can be all the way from 1 minute to 14 days, but remember, once the messages are read, they are deleted from the SQS queue. In terms of pricing, it's very different from Kinesis. You're going to pay per API request, and you're going to pay for the network usage you're due as well. Now, in terms of SQS security, well, we get SSL encryption in flight if we use the HTTPS endpoint for SQS, which is by default. And we can have server-side encryption using KMS. For example, we can set the master key we want to use, and then SSE, the KMS, will directly encrypt the body of the message we send to SQS, but not the metadata itself. So message ID, timestamp, and attributes will not be encrypted by server-side encryption. The IAM policy must allow the usage of SQS, so you can define which user can send data to which queue. And we can, on top of it, set an SQS queue access policy if we want to restrict the security further down. It can get finer grain control, for example, over the IP, or we can control over the time the requests that come in. So that's it for SQS, just a high-level overview. You don't need to remember all these details I just gave you, just remember the general idea, the limits, all that stuff. I hope that was helpful, and in the next lecture, we're going to compare Kinesis data streams and SQS. So see you in the next lecture. So going into the exam, the important thing for you is going to know when you should use Kinesis and when you should use SQS. That's really the important thing that I want to drive home today with you. So Kinesis data streams means the data can be consumed multiple times by many consumers. And the data will be deleted after the retention period going from 24 hours to 1 year. The ordering of the records is preserved at the shard level, even during replay. So there is an ordering constraint right away baked into Kinesis. And because you can have multiple applications reading from the same stream independently, it's called a pub/sub. Basically, you can use Spark or stuff like this to do something called a streaming MapReduce to query the data, process it, and so on. There's a checkpointing feature that you can use with the KCL that integrates with DynamoDB if you wanted to need to track the progress of your consumption. And the shards, the capacity that must be provided ahead of time. We can have shard splitting or shard merging if you want to increase or decrease the number of shards we have, but we have to specify in advance how much throughput we expect to go in our Kinesis data stream. For SQS, well, it's a queue and it's used to decouple applications, and we only get one application per queue. We cannot get more than one because the records are deleted after consumption. The message will be reprocessed independently for a standing queue, so that means that there is an out of order ordering issue that can happen for you. But if you want to have ordering, you can have FIFO queues, but these queues will have decreased throughput, remember, up to 3,000 messages per second. You also have the capability to delay messages, and you have a dynamic scaling of load, so it's a no-ops. You don't need to say in advance how many messages you're going to get in SQS versus Kinesis. Finally, remember, Kinesis data stream has a message payload size of maximum 1 megabyte, whereas SQS is 256 kilobytes. So I think the differences are pretty clear in this slide. I mean, the use cases are different, but here's a table if you needed even more help. So here I compare Kinesis data streams, Kinesis data firehose, Amazon SQS standard, and Amazon SQS FIFO in the same table. So all of those are managed by AWS. Kinesis data streams will provide you ordering at the shard key level. Kinesis data firehose does not provide you any ordering. SQS standard does not provide you any ordering. And Amazon SQS FIFO, if you specify a group ID, you will get ordering per group ID. In terms of delivery, Kinesis data stream is at least once, so is firehose, so is SQS standard, exactly once for SQS FIFO. You can replay data only for Kinesis data streams, not for firehose and not for SQS.
The maximum data retention is 365 days for data streams, between 1 day and 1 year.
Data Firehose does not have any data retention because it's used to deliver data. And SQS can have up to 14 days to retain your data. In terms of scaling, well, you get 1 megabyte per second for producer, 2 megabyte per second for consumer, enhanced fan out or not. And then for Firehose, you have no scaling needed. It will scale for you. SQS as well. And if you use SQS FIFO, you have 3,000 messages per second with batching, which is a soft limit. You could increase that if you wanted to. Now, the max object size for Kinesis data streams is going to be 1 megabyte. For Kinesis data Firehose, it's going to be 128 megabytes. That's the max buffer size you can set. So the destination can have maybe S3, can have an object of 128 megabytes being written to. And for SQS, it's 256 kilobytes and more if you use the extended SQS clients. Okay, now that's for all the technicality, but what about use cases? Maybe that makes more sense to you. Well, the SQS use cases will be to process orders, to process images, to autoscale queues according to messages, to buffer and batch messages for future processing or inserting into a database, maybe to do some request offloading. So it's more of a development-driven workflow, whereas for Kinesis, it's going to be more for big data. So you're going to get fast log and event data collection and processing, real-time metrics and reports, mobile data capture, real-time data analytics, gaming data feed, complex stream processing, or a data feed from the Internet of Things. So this is, I think, the most important thing here. Kinesis is going to be used for big data streaming, whereas SQS is going to be used for decoupling of your applications more from a developer's perspective. Okay? So I hope that really helps. This is all you need to know going into the exam. You really need to be able to differentiate SQS and Kinesis. I hope that was helpful, and I will see you in the next lecture. Okay, so we are getting into IoT. IoT stands for Internet of Things, and this is quite a light subject at the exam, but you never know the kind of questions you may get, so I want to give you a high-level overview of all the services offered by IoT. You'll see in the end it makes a lot of sense. This slide will basically explain anything you need to know, then I'll do a small deep dive on each feature. So IoT stands for Internet of Things, and because it's Internet of Things, in AWS, an object is called a thing. So an IoT thing can be whatever you want. Like here, it's a thermostat, but it could be a bike, it could be a car, it could be a light bulb, it could be anything you want really. So it's just going to be a connected device to your AWS infrastructure. And so we configure these devices and we want to retrieve and interact with them. So we want to retrieve data and interact with them. So how does it work? Well, this IoT thing is going to be registered with our IoT cloud in AWS. So it's going to have a thing registry, and a thing registry will help giving the device an ID, making sure it's well authenticated, security, all that stuff. Okay? Then this IoT thing needs to communicate with our cloud, and through this, it uses something called a device gateway. A device gateway is a managed service which allows you to communicate with your IoT things. Now, when your IoT thing, for example, wants to report something, say, for example, the temperature is now 30 degrees Celsius, it's going to send a message to an IoT message broker. So a message broker is going to be like an SNS topic. It's going to be sending a message, and that message will be sent to many different destinations. For example, say we wanted to take that message, make it go through a rules engine, and this rules engine is saying, whenever the IoT thing sends you a message, send that message maybe to Kinesis, SQS, Lambda, or so many different other targets. So with this rules engine, we have the possibility to send our message to different targets. But you can do other things. You can also integrate with something called an IoT device shadow. And this device shadow is literally a shadow of your device. That means that even if your thermostat right here is not connected to the internet, you can change its state here on the device shadow. For example, we can say, okay, we want the temperature to now be 20 Celsius. And whenever that device will get reconnected, then the device shadow will say, by the way, you need to be 20 Celsius now. So all of this at a high level is what you need to know from an IoT perspective. I would say the most important things is going to be the thing registry to know that there is security, the IoT message broker, the rules engine, and the device shadow. Once you get this architecture, it makes all sense. Now I'm going to give you a little bit more details around each of these features just for your own curiosity, but at a high level, you know enough already. Now, before we go into the deep dive lectures, I want to give you a little bit overview on AWS Cloud for the console for IoT, because I think it has a really cool tutorial, so follow me. So for IoT Core, if you go to services, you will see all the categories here. I just want to call your attention to Internet of Things on the right-hand side. It has a lot of different services. Now, thankfully, you don't need to know all of them. The only thing we'll focus on today is IoT Core. So all these things except Greengrass that I will describe very quickly, all these things you don't need to know. So let's go to IoT Core and choose your region, whatever region you have. Here, I'm not greeted with a tutorial because I did it already. But so let's go to the bottom left, and you see in the bottom left there is a Learn button here that I'm going to click on. And the reason I'm doing this is that because there's a small tutorial right here that is really well done, and I think it's amazing for me to use this as a learning tool for you. So let's go through this tutorial, and I'll be able to give you one more time the high-level overview of all the things I just described, but this time there will be animated diagrams, okay? So let's start this tutorial. So this is the device gateway. So the device gateway basically enables your device to securely communicate with the AWS's cloud, okay? So say, for example, we have two things, right? There's a connected light bulb right here. This is a light bulb that's connected to our device gateway. And we also have a control unit. Here, maybe it's in our house, and we can set red, green, or blue for our light bulb, okay? And it's connected to our device gateway. So they're connected, and so if I click on green, for example, it's going to send a message all the way to the device gateway and back into my light bulb. And now my light bulb is green. If I click on blue, my light bulb becomes blue, and red, obviously, it will become red. So as you can see, my two devices here, even though they're in my house, they don't communicate right away with each other. What they do communicate with is this device gateway, which has a message broker inside of it, and they communicate through this device gateway to be able to change each other's states. So again, green will be sent to the device gateway, back into the light bulb. Same for blue. So this shows really well the concept of what a device gateway is. Okay, that's the first step. Hopefully that makes sense. Next is the rules engine. So here you're able to define a bunch of rules, and you would have to write them around what happens when my control unit sends a message to my device gateway, what should happen, and how should the message change. So you can have very complicated rules, but here they show us a rule said blue should be turned into green. So let's have a look. If we click on red, well, my light bulb is red. If we click on green, my light bulb is green. But if we click on blue, you see here it came blue and it came out green. Let's do it again. Blue, green. Because the rules engine here said the blue should be transformed into green. I can switch that off, that rule, and now if I send blue, well, it turns out that my light bulb is going to be blue. So the rules engine contains a bunch of rules that you can define, allowing you to modify the behavior of your devices based on some rules you define. So here, again, if I click on blue, it's going to become green, okay? Hope that makes sense, and you can also play with it. Now with this rules engine, we can set up rules actions. And actions are really cool. Actions is what I had in my graph before, saying that when we define these actions, we can send data to Kinesis, SQS, Lambda, etc. So here, they're showing that we have the blue to green rule before. So again, if I click on blue, it's going to become green and go back. But now if I do red, red is going to be sent to all the things on the right-hand side. So it's going to be sent to my mobile device, to my AWS Lambda function, and to a database as well. So let's click on red. And as you can see, the red message goes into all the directions because of this rule right here. So if you click on red, it goes into my mobile device, my Lambda function, and my database. If I turn off this rule, again, you see it's not connected anymore. So if I click on red, it will just go to my light bulb. So you can play around here as well and see what rules does what, and so on. So here, what we need to remember is that the rules engine allows us to send data to many different targets within AWS. So as you can see, my devices don't interact directly with AWS Lambda. It goes through my device gateway and message broker. Okay, next is a concept of device shadow. Now, device shadow is really, really important to understand and really weird at first to learn about. So hopefully I'll make a good way of describing it to you. So the device shadow is going to be a shadow of your device. So here's my real device. This is my real light bulb, and you can see it's red. And my device shadow in my cloud, you see it's within the blue cloud. The device shadow is also red. Now, if I click on blue, I'll just deactivate every rule for now. If I click on blue, then my light bulb is blue and my device shadow is blue as well. So like the name indicates, my device shadow is literally a shadow of my device. So why do we need this? Well, for example, say that the Wi-Fi in my home stops, or my light bulb stops communicating with the AWS cloud. Now I want to change the color of it to blue. So I'll say, okay, you should become blue. And only the shadow here gets updated. Okay? And that means that within the AWS cloud, my device is supposed to be blue. But this one doesn't know it yet because it's not connected to the cloud anymore. But as soon as it gains back connection, the device shadow will send a message back to it saying, hey, by the way, you should be blue. And it becomes blue. So basically, to control the state of devices that are even offline, we can use the device shadow. For example, I'll set it to red. Okay, my device shadow is red now. And anytime I will turn back on my light bulb, boom, it becomes red. So the device shadow is a way for you to say you are able to control your offline devices by using the device shadow in AWS Cloud. Okay, now you can just turn on all the rules and have some fun and play. But the cool thing here is that you can turn on and off the switches to see what would happen with the device shadow, the rules engine, and so on. Finally, it's saying this is cool when you have a light switch in your house, but you can also program an application, for example, this one, which allows you from your mobile device, say your iPhone, to control the light bulb. And you're saying, okay, I want it to be green. It will send a REST API call directly into the IoT cloud, and my light bulb will become green. So I think this is a really good animation and overview of how the entire IoT solution works. I hope you liked it, and in the next lecture I'll do some deep dive into all these services, but hopefully that's a good enough introduction. All right, I will see you in the next lecture. Okay, so let's talk now about the IoT device gateway in depth. So the device gateway, as said before, is an entry point for your IoT devices connecting to AWS, and it allows the devices to securely and efficiently communicate with the AWS IoT cloud. It supports many protocols such as MQTT, you have to remember that, WebSocket, and HTTP 1.1 protocol. It's fully managed and will scale automatically to support over 1 billion devices. So if you have a very successful company, IoT device gateway should work for you. You don't need to manage any infrastructure, so it's like a serverless service. So for example, here we have a connected bike, it's our thing, and it's sending MQTT messages into our device gateway. Remember that the device gateway is in the AWS cloud, whereas your thing is in the real world. Okay, so device gateway, I think super easy. The name is also very self-explanatory. Now message broker. So message broker is a pub sub and it's within the device gateway, and you can publish messages to it with low latency. And this is how devices communicate with one another. So remember in the introduction before, my switch and my light bulb did not interact with one another directly. My switch was sending messages to the AWS cloud, and my light bulb was reading these messages from the AWS cloud. This is how the IoT message broker works. Again, the messages are sent using MQTT, WebSocket, or HTTP 1.1 protocol, and they're published into topics. So it's called an IoT message broker topic, just like we have SNS topics. The message broker will then forward the messages to all the clients that are connected to that specific topic. So let's have a look. Our thing sends an MQTT message to message gateway, makes it through to the message broker, and then anything connected to the message broker will receive that message. So we can think about how we can orchestrate all our devices, all our things using this message broker. Now we have thing registry, which is basically the IAM of IoT. And so all connected IoT devices will be represented within the IoT registry, and it will organize all the resources associated with each device in the AWS cloud. Each device will get a unique ID, and we can have support for metadata for each device. That means it can be a Celsius device or a Fahrenheit device, that kind of stuff. We create X509 certificate to help IoT devices connect to AWS, and we'll see authentication in the very next slide. And then we're able to group these devices together and apply directly permissions to the group. So this is all very, very similar to IAM in the end, right? So remember, just thing registry registers iOS devices. Now, how does authentication work? Well, once our device is basically registered with the thing registry, you have 3 possible methods for things. The first one is that you get these X509 certificates and you load them securely onto the thing. And then using some mutual authentication, basically it will authenticate to the device gateway. That uses AWS SecV4 and custom, or you can use custom token with custom authorizers. So you have very different ways of authenticating your thing with a device gateway. If you have a mobile app, you can use Cognito Identity, and if you have web, desktop, or CLI things, you could use IAM or federated identities. Basically, the last two are AWS standard. The first one is that you load your certificate that you've created on the AWS cloud directly onto the IoT device, and they will have a mutual authentication with the device gateway. As far as authorization goes, we have IoT policies, and they're basically attached to each thing in the thing registry, and that allows us to basically enable or revoke these policies on the device at any time. The IoT policies are JSON documents. They look just like IAM documents, and they can be attached to groups instead of individual things if you want to use groups to leverage and have an easier management of authorization. The IAM policies, on the other hand, they're attached to users, groups, and roles in AWS, and they're used when you have IoT AWS API. So remember, your devices are ruled by AWS IoT policies, whereas your users, roles, and groups, just like in AWS normal, are ruled by IAM policies. Okay, now device shadow. Device shadow, remember, that was this really weird concept where even if a device was offline, we could change its shadow in the AWS cloud, and as soon as the device came back up online, it would look at what the shadow state is and copy it. So a device shadow is a JSON document representing the state of a connected thing, and we can set the state to a different desired state, for example, light on, light off, or light blue, light green, light red. The IoT thing will retrieve the state when online and adapt automatically. So here's an example again. Our light bulb is off, and its device shadow in the AWS cloud is that it's off. Then we change the device shadow using the AWS API, for example, our mobile application to on. So we're saying, okay, our device should now be on. We set the shadow to on, and automatically there will be a synchronization on state, and my light bulb will become on. So this is how, in the AWS cloud, using device shadows, we can basically change the state of our things in the real world. Rules engine is, to me, I think the most important thing going into the AWS exam. So the rules are defined on the MQTT topics, the message broker topics. Rules say when it's triggered, and action is what it does. The rule use cases can be so many. I won't read them all to you, but basically you can filter or change device data. You can send to DynamoDB database, S3, SNS, SQS, Lambda, Kinesis, Elasticsearch, CloudWatch, Amazon Machine Learning, and more. Basically, all these rules, when you define them, you just apply an IAM rule, and it can send data all the way from your IoT devices all the way into the very, very end, which is Kinesis, for example. So let's have a look at the graph. IoT topics will have rules actions, and these rules actions can send data, for example, to Kinesis, DynamoDB, SQS, SNS, S3, and AWS Lambda. So in the exam, if they ask you how do we get IoT devices to send data to Kinesis, the answer is do not use directly a put record on the device. Instead, send it to an IoT topic and define an IoT rule action to send data all the way to Kinesis. Okay, last but not least, IoT Greengrass. IoT Greengrass brings the compute layer directly to the device. So that means we have our local device and we can run Lambda functions on the device. So for example, our coffee pot can be a smart coffee pot and run Lambda functions. The really cool thing with this is that you can pre-process the data, execute predictions maybe based on ML models, or keep the device data in sync. You can also use this to communicate locally between devices if you dearly wanted to. You can also operate offline, so the Lambda functions need to be connected to the AWS cloud, and you can deploy functions directly from the cloud to the devices, which allows you to update the devices at any time if you wanted to. So this is all you need to know for IoT. I know this was a deep dive. Don't need to know all the details I just said, but getting a general understanding to me is very important. Now, I can't really do a hands-on with you because I don't have an IoT device, and so do you. You don't have an IoT device, but hopefully that high-level knowledge will allow you to answer with confidence the exam questions that come up on IoT, and there are not that many. Okay? So I hope that was helpful, and I will see you in the next lecture. So let's say you wanted to migrate a database from your on-premise systems to the AWS cloud. In this case, you should use DMS for Database Migration Service. It's a quick and secure database service that allows you to migrate your database from on-premise to AWS, but the cool thing is that it's resilient and it's self-healing. And all alongside the migration, the source database remains available, and it supports many types of engines, such as homogeneous migrations, so from Oracle to Oracle or Postgres to Postgres, but also heterogeneous migrations, for example, if you want to migrate from Microsoft SQL Server all the way to Aurora. And it supports continuous data replication using CDC, which is Change Data Capture. Finally, to use DMS, you need to create an EC2 instance, and that EC2 instance will perform the replication tasks for you. So very simply, your source database may be on-premise, and then you're running an EC2 instance that has the DMS software, and it will pull the data from the source database in continuously and put it in the target database. So the question is, what are the sources and what are the targets? You don't need to remember them all, but it's a good idea to just see them once. The first one is going to be on-premise and EC2 database instances, such as Oracle, Microsoft SQL Server, MySQL, MariaDB, PostgreSQL, MongoDB, SAP, and DB2. Again, you don't need to remember everything, that's fine. Azure, which is going to be for Azure SQL databases, RDS, which is all the databases including Aurora, and Amazon S3. And the targets is going to be on-premise and EC2 instances such as Oracle, Microsoft SQL Server, MySQL, MariaDB, Postgres, and SAP. Amazon RDS, Redshift, DynamoDB, S3, Elasticsearch Service, Kinesis, and DocumentDB. So as I said, you don't need to remember everything, but the idea is that you can transform a source which is on-premise to a target which is usually AWS, and these targets are all the common databases on AWS. So what if the source database and the target database do not have the same engine? Then you need to use something called AWS SCT for Schema Conversion Tool, and it will convert the database schema from one engine to another. So for example, if you're using an OLTP, we can migrate from SQL Server or Oracle to MySQL, Postgres, SQL, or Aurora. As you can see on the left-hand side, the database engine is different from the one on the right-hand side. But also you can transform from analytics processes such as Teradata or Oracle all the way to Amazon Redshift. So the idea is that here, the source database has a different engine than the target database. In the middle, we have DMS, but it's now also running SCT, or Schema Conversion Tool. And the thing to know going into the exam is that you do not need to use SCT if you are migrating the same database engine. So if you're doing on-premise PostgreSQL to RDS PostgreSQL, it is the same database engine, it is PostgreSQL, and so therefore you will not use SCT. But if you're doing something such as Oracle to Postgres, then you will need to use SCT. So just so you know, the database engine is PostgreSQL, but RDS is just the platform that we're using to run this database engine.
So how would you go to set up a continuous replication for DMS? Well, you would have your corporate data center, for example, with an Oracle database as a source, and an Amazon RDS database from MySQL DB as a target. And as we can see, we have two different kinds of types of database. So in this case, we have to use SCT, otherwise it will not work. So the Schema Conversion Tool. So we set up a server with AWS SCT installed, and we can set it up on premises. This is best practice. And then we will do the schema conversion into our Amazon RDS database running MySQL. Then we can set up a DMS replication instance that will do the full load and the change data capture CDC to have continuous replication. And so it will perform the data migration by reading the database on premises, the source Oracle database, and inserting the data into your private subnets. That's it. So that's all you need to know for DMS. This is for Database Migration Service. Remember, you need to use SCT whenever you have two different kinds of databases that you're migrating from. So that's it. I will see you in the next lecture. Now let's talk about Direct Connect. And you may also see it as DX in the exam. So it provides a dedicated private connection from a remote network into your VPC. So you need to set up that dedicated connection, and it is using an AWS Direct Connect location. You also need to set up a virtual private gateway on your VPC side to make the connectivity between your on-premises data center and AWS. The idea is that on the same connection, you can access both public resources such as Amazon S3 and private resources such as EC2 instances using the public VIF and the private VIF. So what are the use cases for Direct Connect? Well, you get increased bandwidth throughput. That means that if you're working with large data sets, it's going to be faster because it doesn't go over the public internet. And also you're going to have lower cost because you're using a private connection. Also, if you have connectivity issues using the public internet, while using Direct Connect, you get a more consistent network experience, again, because it is private. So this is especially helpful if you have applications using real-time data feeds. Finally, it supports hybrid environments because you have connectivity between your on-premises data center and the cloud. It supports both IPv4 and IPv6. So let's look at a diagram of Direct Connect. So we have a region and we want to connect it into our corporate data center. So for this, we're going to commission an AWS Direct Connect location. They're physical locations that you have to find, but it's all obviously on the website of AWS. And there's going to be a Direct Connect endpoint, and there's going to be a customer or partner router that you have to rent from a customer or partner cage. So you have two cages in this Direct Connect location. And then on your on-premises data center, you're going to set up a customer router with a firewall. Now you're going to set up a private virtual interface, so private VIF, first to access your private resources into your VPC. So to do so, you set up the private VIF in between all these locations into a virtual private gateway. And this virtual private gateway is attached to your VPC. And through the private VIF, you are able to access your private subnet with your EC2 instances. And as you can see, all these things happen privately, so you need to set up that connection manually. It can take a month to set up, but none of this goes over the public internet. It is all a private connectivity. The alternative is to connect to public services within AWS, such as Amazon Glacier or Amazon S3. And for this, you're going to set up a public virtual interface or public VIF. And so it goes through the same path, but it doesn't connect into a virtual private gateway. It connects directly into AWS. So what if you want to connect to one or more VPCs in different regions? For this, you must use a direct connect gateway. So we have an example where we have two regions and they have two different VPC with two different CIDRs. And we want to connect our on-premises data center into both VPC. So we're going to establish a direct connect connection. Then using the private VIF, you're going to connect it to a direct connect gateway. And this gateway will have a private virtual interface into a virtual private gateway in the first region and another one in the second region. So using the setup, we can start connecting to multiple VPCs and multiple regions. Okay, now let's discuss the connection types for direct connects. We have a dedicated connection. It could be 1 gigabits per second or 10 gigabits per second capacity. And we get a physical Ethernet port that is dedicated to us. And first, we need to make a request to AWS, and then it will be completed by an AWS Direct Connect partner. Or we can get a hosted connection, and they come in different flavors, such as 50 megabits per second, 500 megabits per second, up to 10 gigabits per second. And again, we make connection requests via the AWS Direct Connect partners, and then we can add capacity on demand. So we can add or remove capacity on demand, so it's a bit more flexible than a dedicated connection. And so we can get 1, 2, 5, 10 gigabits available at select locations. And to set up either a dedicated or a hosted connection, the lead times are often longer than 1 month to establish a new connection. So in the exam, they will ask you questions around, hey, we want to transfer some data within a week, and we want it to be fast. So an answer cannot be direct connect because direct connect takes often more than 1 month to establish. So you need to look into the question whether or not there is already a direct connect established and whether or not the time to transfer the data is less or greater than 1 month. Now, when you have a direct connect, there is no encryption, so data in transit is not encrypted, but it is private because it is a private connection. And so if you wanted encryption on top of it, you can set up direct connect to be alongside a VPN to provide IPsec encrypted private connection. So it's good to get an extra level of security, but it's slightly more complex to put in place. So the setup is to get the same direct connect location, but then on the connection, you're going to set up a VPN connection on top of it to have encryption for your direct connect. And therefore, all the traffic between your corporate data center to AWS is going to be encrypted. Now, one last thing that can come up in the exam is around resiliency for direct connects. So we have two modes of resiliency and architectures, and you need to know them both because they will be coming up at the exam. You have high resiliency for critical workloads, where we set up multiple direct connects. So we have two corporate data centers, and we have two different direct connect locations, and this gives us some redundancy. So in the first case, we have a private VIF here, and we have a private VIF here, and so here we get one connection and multiple locations. And so if one of the direct connect location goes down, then at least we have some backup direct connect location somewhere else. And so this gives us high resiliency, and this is good for critical workloads. But if you want to get maximum resiliency for critical workloads, and I emphasize the word maximum because it can come up in the exam, then you're going to have to set up, again, two direct connect locations, but this time each direct connect location will have two connections independent to give you maximum resiliency. So in this use case, we have four direct connect locations, four connections across two locations, going into AWS. And so maximum resilience is achieved by using separate connections terminating on separate devices in more than one location. So that's it for direct connects. I hope you like this lecture, and I will see you in the next lecture. So now let's talk about the AWS Snow family. So it represents a highly secure portable devices that has two use cases within AWS. Either it's used to collect and process data at the edge, or to migrate data in and out of AWS. So we have two use cases, the data migration, and for this we have three different types of devices within the Snow family. We have the Snow Cone, the Snowball Edge, and the Snowmobile. And for the second use case, edge computing, we have the snow cone and the snowball edge. So we'll first tackle the data migration subject and then the edge computing. So why do we want to do data migration with the AWS Snow family? Well, if we look at the time it takes to transfer a lot of data over the network, it can take a lot of time. So for example, if we want to transfer 100 terabytes over a 1 gigabits per second network line, it will take us 12 days to achieve it. Okay. And so obviously, if we do a petabyte, it will take forever and so on. So as we can see, sometimes we just want the data to get to AWS fast. And the challenge is that sometimes, on top of having a small network transfer, you have limited connectivity, limited bandwidth, sorry. Transferring data over the network may cost you some money. Okay. It's not free to use a network. It could be that also the bandwidth is shared. For example, if you download a video from AWS and you download 10 terabytes of data, maybe you're going to block your entire office because you're maximizing the bandwidth within your office. And then maybe the connection is not stable enough, so you have to retry and so on. So all these reasons make a case for Snow family. So the Snow family are offline devices that allow you to perform data migrations. So AWS will send you an actual physical device by the post office, and then you load your data onto it, and then you send it back to AWS. So the rule of thumb is that if it takes more than a week to transfer data over the network, then you should use a snowball device, for example. So to really explain how that works, let's take an example. If you wanted to directly upload a file into Amazon S3, we have the client sends the data into Amazon S3. Very easy, right? But with the Snow family, for example, with the snowball device, the client requests a snowball device. We receive it via the post, okay? AWS will deliver the device to us. We load the data directly onto the devices locally, and then we ship back the device to AWS into an AWS facility. Then they will take the device and they will plug it into their own infrastructure, and then the data will be imported or exported based on what you want to do to an Amazon S3 bucket, and you're good to go. So really, it is a way to transfer data to AWS, but through the physical route, not the network route. Okay, so now what sort of devices do we have? We have the Snowball Edge. And Snowball Edge is a huge box, as you can see, and it is going to be used to move terabytes or petabytes of data in and out of AWS. It's going to be an alternative to moving data over the network, as we've seen. We're going to pay per data transfer job, and the interface within the Snowball Edge is going to provide a block storage or Amazon S3 compatible object storage. So we have two flavors for the Snowball Edge. We have the Snowball Edge storage optimized, which is going to give us 80 terabytes of hardware hardware disk capacity, which works for block volume or S3 compatible object storage. And we have the Snowball Edge compute optimized, which is going to give us 42 terabytes of HDD capacity. So really, if we want to have more storage, obviously, we want to get the flavor that is called Snowball Edge Storage Optimized. So the use case for a Snowball Edge for data transfers so far is to do a large data cloud migration, to decommission a data center, or maybe to do disaster recovery by backing up your data into AWS. So that's for the first option. The second option is called AWS Snow Cone. And Snow Cone is a cute little name because it is a cute little thing. This is a much smaller device. As we can see an Ethernet port on it. So Snow Cone is much smaller than a Snowball Edge. And this is a small, portable computing anywhere, rugged and secure, and it can withstand harsh environments. So it can go in desert, it can go in the water. It's really, really light and secure. So this device is going to be used for edge computing, storage, and data transfer, but obviously of much smaller size. And as such, you can store 8 terabytes of storage on a Snow Cone. So much less, about 10 times less than the Snowball Edge storage optimized device. So you should use a Snow Cone where a snowball does not fit. So for example, in space-constrained environments, you can even put a Snow Cone on top of a drone if you wanted to. You must provide your own battery and cables, and it can be sent back to AWS offline, or you can even connect it to the network, and it will use AWS data sync to send the data back over the network. So imagine you have a snow cone into an environment that doesn't have any network connectivity. It will collect and collect and collect and collect data. And then you go back home, you go to your data center, you take the snow cone and you plug it into your data center, and automatically the data is being transferred to AWS. Or you can just send it back again offline to AWS, but you have two options with the snow cone. And then Snowmobile is an actual truck. So when they announced it, they actually took a truck on stage to show that it was an actual truck that is going to transfer data. And so with the Snowmobile, you can transfer exabytes of data. So 1 exabyte is 1,000 petabytes is 1 million terabytes. And each Snowmobile will have 100 petabytes of capacity. So if you wanted to reach 1 exabyte of data, you need to order 10 Snowmobiles. It's high security, it's temperature control, there's GPS, 24/7 video surveillance, so it's quite a secure way to transfer your data. And it's a better use case than Snowball if you start transferring more than 10 petabytes of data. So as a summary, for data migration, we have 3 options. We have Snowcone, Snowball Edge, Snowmobile, and each come with different storage capacity, so 8 terabytes, 80 terabytes, and 100 petabytes. The migration size that's recommended by AWS is a Snowcone is up to 24 terabytes. For Snowball Edge, it's up to petabytes, and it's offline because you have to send it back to AWS. And for Snowmobile, the use case is up to exabytes of data. Data Sync agent is pre-installed on a Snowcone because you can plug it to a network and have Data Sync send the data over the network to AWS as well. And for Snowball Edge, you can do storage clustering, so you can put up to 15 Snowball edges together to increase the storage size. Okay, so how do we use a Snow family device? Well, you request the device from the console for delivery, and we'll see this in the hands-on. Then we install the Snowball client, or we use AWS Ops Hub that we'll see in this lecture on your servers. Then we connect the Snowball to the servers and start copying the files in the client. Then we ship back the device when we're ready. It will go straight to the right AWS facility thanks to an e-ink marker. And the data will be loaded onto an S3 bucket. And then the Snowball will be completely wiped according to the highest security measures. So that's for the data migration. And that was originally one and the only use case for Snowball devices. But the second use case now for the Snow family is called edge computing. And so edge computing is when you process data while it's being created at an edge location. So what is an edge location? Well, an edge location is anything that really doesn't have internet or that is far away from a cloud. So for example, if you have a truck on the road, or if you have a ship on the sea, or a mining station underground, all these things can be called edge locations because they can produce data, but they may not necessarily have internet connectivity. So either limited connectivity or no internet access, or no access to computing power. And so you may still want to run computation, data processing at these locations. And for this, we need edge computing. And so to do edge computing, we can order a Snowball Edge device or a Snowcone and have it embedded into these edge locations and start doing edge computing. So the use cases of edge computing is to pre-process data, do machine learning at the edge, so without it going back to the cloud, transcode major streams in advance, and eventually, if need be, if you need to transfer the data back into AWS, you can ship back the device for your Snowcone or your Snowball Edge. So really, you start processing the data very, very close to where it's being created, and then you ship it back to AWS. So for edge computing, what do we have? We have the Snowcone, and it comes with 2 CPUs, 4 gigabytes of memory, has wired or wireless access, so Wi-Fi. It's powered by USB-C, and an optional battery. Then for Snowball Edge, it's compute optimized. So we have 2 different flavors again. So the compute optimized one has 52 vCPUs, 200 gigabytes of RAM, and an optional GPU if you wanted to do video processing or machine learning. We have 42 terabytes of usable storage. And for the Snowball Edge that is storage optimized, we have 40 CPUs, so less, and 80 gigabytes of RAM, so again, less RAM as well. We have object storage clustering available for the storage. And all of these devices can run either EC2 instances within them or Lambda functions using the service called AWS IoT Greengrass. And if you do edge computing, then you may want to have these devices in your facilities, in your trucks, in your boats for a very long time. And so therefore, you have long-term deployment options where you can get a discounted pricing if you borrow these devices for 1 or 3 years. Finally, for the Snow family, there is UpSub. So historically, when you were using these devices, you needed a CLI, so a command line interface tool, to deal with them, and it was very, very difficult. And so AWS recognizes that, and so they've created UpSub, which is a software that you install on your computer or laptop. So it's not something you use on the cloud; it's something you have to download on your computer. And then once it's connected, it's going to give you a graphical interface to connect to your Snow devices and configure them and use them, which is very, very handy. So this allows you to do unlocking and configuring single or cluster devices, transferring files, launching and managing instances, so EC2 instances running on Snow family devices, monitor device metrics, and launch compatible AWS services on your devices, for example, EC2 instances, use data sync, or a network file system. So that's it for the Snow family. I hope you liked it, and I will see you in the next lecture. Now let's talk about MSK, because MSK is starting to appear on the data and analytics specialty exam. You don't need to know how to use Kafka, so because it's quite complicated actually to use Kafka, so there will be no hands-on on this, but you need to know how MSK works, what's the architecture, and the differences versus Kinesis. So Kafka is an alternative to Kinesis, and there will be a lecture dedicated to Kafka versus Kinesis in the next lecture, because the exam will mainly try to make you choose between Kafka and Kinesis based on some scenario. So what is Kafka though in MSK? So MSK is a fully managed Apache Kafka service on AWS, which allows you to create, update, and delete Kafka clusters. And in that case, Amazon MSK will create and manage Kafka broker nodes and Zookeeper nodes for you. You deploy your MSK cluster in your VPC. It's multi-AZ up to 3 for high availability. There is automatic recovery from common Apache Kafka failures, and the data is stored on EBS volumes. The idea is that MSK and Kafka is a replacement for Kinesis, where you have, the same way, your producers and your consumers of data. But the power of Kafka is that you can create some custom configurations for your cluster. For example, one that can come up in the exam is that by default, the message size is 1 megabyte in Apache Kafka, but you can configure Apache Kafka to be able to send and receive large messages, for example, up to 10 megabytes into your cluster after doing some custom configuration. And that is a big difference with Kinesis, because Kinesis has a hard limit of 1 megabyte for the message size. Now, at a high level, you will recognize the Kafka cluster architecture to be very similar to Kinesis. So now we see what goes in your clusters. So you have brokers, and they're called Apache Kafka brokers, and data will be replicated within them. So in this example, I've shown you 3 brokers in your Kafka cluster. Now, producers can be your code and could be whatever you want. You can create producers to take data from Kinesis and put it in Kafka clusters, or IoT or RDS, etc. So you just have to write some application to take some data and put it and send it into what's called a Kafka topic. Now, Kafka topics are replicated. So this is how your data is safe across multiple availability zones. And so once it's written to a Kafka topic and replicated, then consumers, which will be your code, will be pulling from your Kafka topics, and then consumers can do whatever they want. They can do some logic, stream processing, or send the data into target data sources such as EMR, S3, SageMaker, Kinesis, RDS, etc., etc. So as you can see, it's quite similar to Kinesis. The difference is that the APIs are different, the tooling is different, and that Kafka is going to be way more configurable, which will allow you to get around some Kinesis limits. So in terms of configuration, you choose a number of availability zones. So 3 is recommended, or 2. Then you choose the VPC and subnets. This is a private cluster. You choose the broker instance type, for example, an M5 large EC2 instance, the number of brokers per AZ, and you can add brokers over time. And this gives you, in the end, 1 Zookeeper per availability zone and 1 Kafka broker per AZ. So in this example, or 2 per AZ, for example, in this example. So we have 3 Zookeeper nodes and 6 Kafka brokers and 3 AZ in this example. Finally, you choose the size of your EBS volume between 1 gigabyte and 16 terabytes, which allows you to retain data for as long as you need based on the time requirements. Again, maybe giving you a little bit more flexibility versus Kinesis data streams. Okay, now security is very important in Apache Kafka, and you will be asked maybe one question about it at the exam. So let's take an example of a cluster with 3 brokers. So we can get encryption in flight between each brokers using TLS. So by default, it's enabled, but you can disable it if you wanted to for performance improvements. You also get optional TLS encryption in flight between the clients and the broker. And again, by default, this is enabled, but you can disable it as well for performance reasons as well. You get at-rest encryption for your EBS volume using KMS, so this is enabled. Now for network security, you can attach security groups to your Kafka clients to ensure that network security is made between your brokers and your EC2 instance. And most importantly, is going to be around authentication and authorization. And this is very important. So this allows you to define who can read and who can write to which topics in your Kafka cluster. And so there are three kinds of mechanisms today in Apache Kafka. The first one is called mutual TLS. So that means that TLS certificates are used for encryption, but also for authentication. So this is why I wrote mutual TLS auth-n for authentication. And in that case, when you use this mechanism, you have to use Kafka ACL, so access control list, to do the authorization at the topic level. And Kafka ACLs are a mechanism within your Kafka cluster. You can also use something called SASL Scram, which is, to make it very simple, username password for authentication. And again, you would need to use Kafka ACLs for authorization. Or you can use IAM access control. And IAM access control allows you to do both the authentication and the authorization using IAM policies. So this is sort of what you get with Kinesis data streams. So this is something, again, you have to know going into the exam to do Kafka security. Okay, so the one thing you need to know, though, is that Kafka ACLs for mutual TLS and SASL scrams cannot be managed using IAM policies. They have to be defined from within your Kafka cluster. Okay, so that's it for security. Next, we have monitoring. So we have CloudWatch metrics and get 3 level. We get basic monitoring to get cluster and broker level metrics, enhanced monitoring to get more broker metrics, or topic level monitoring. So for each data stream within your cluster. And this allows you to get enhanced topic level metrics. You get Prometheus for open source monitoring, which allows you to extract data directly using the JMX exporter or the No exporter using the Prometheus protocol. And broker log delivery can be done to CloudWatch logs, Amazon S3, or Kinesis data streams. So that's it for MSK. Just remember it as a drop-in replacement for Kinesis and a more configurable one. You need to remember the MSK security because it will be asked for you at the exam. And I will see you in the next lecture to talk about Kinesis data streams versus Amazon MSK. So here is a feature about MSK called MSK Connect. The idea is that in the Kafka world, you have something called Kafka Connect. And Kafka Connect is a framework to take data from Kafka and put it somewhere else, or vice versa, to take data from somewhere else and put it in Kafka. And when you use the Kafka Connect framework in MSK, what you can do is to use MSK Connect, which is going to give you a managed Kafka Connect workers on AWS with auto-scaling capabilities. That means that you can deploy the infrastructure of Kafka Connect on MSK Connect, and then you can deploy any Kafka Connect connector to the MSK Connect as a plugin. And so these plugins can be, for example, sending data into Amazon S3, Amazon Redshift, Amazon OpenSearch, Debezium, and so on. And so here's an example. You have the MSK cluster up and running. Then you're going to create your MSK Connect workers thanks to the MSK Connect service, and you will deploy the plugin being the Amazon S3 Kafka connector. And then the Connect workers are going to pull the topic data from your MSK cluster, and then the data will be written to Amazon S3 as a result. And we haven't managed any infrastructure. It's all done by MSK Connect, and it's just configuration on our end. So there's a pricing. Here's an example. You pay 11 cents per worker per hour. And of course, the more data you have, the more workers you're going to need. So that's it for MSK Connect, just introduction, in case you see it in the exam. I hope you liked it, and I will see you in the next lecture. So here is another very short lecture called MSK Serverless. And MSK, as we know, we provision a Kafka cluster and we pay per hour. But with MSK Serverless, we run Apache Kafka on MSK without managing the capacity. And MSK will automatically provision resources and will scale the compute and storage. So it makes it very easy for us to understand what's happening. And so therefore, from a user perspective, all you have to do is to define what topics you want and how many partitions per topic, and you're good to go. In terms of security, you get IAM access control for all clusters. And here's an example pricing. So you're going to pay 75 cents per cluster per hour, which gives you $558 monthly dollars per cluster. Then you're going to pay a pricing per partition per hour, which is about $1 per partition per month. Then you're going to pay per storage, per data in, and per data out. And that is a different way of seeing pricing on MSK and maybe a model that works better for you. Okay, that's it. I hope you liked it, and I will see you in the next lecture. Okay, so in the exam, most likely you will have to choose Kinesis Data Streams over Amazon MSK because AWS likes you to use their products. But it is important that maybe in one or two edge cases, you will have to say that Amazon MSK is the right answer. And for you to know it, you need to know the differences between Kinesis Data Streams and Amazon MSK and the main ones. So in Kinesis Data Streams, there is a hard limit of 1 megabyte per message size, and you cannot go over it. So in Amazon MSK, though, it's 1 megabyte by default, but you can configure for higher, for example, 10 megabytes. And that's going to be a huge difference. So if you see a large message in the exam, this is going to rule out any Kinesis Data Streams answers or Firehose answers and go straight into Amazon MSK. Now in Kinesis Data Streams, it's called Data Streams with shards. And in Amazon MSK, it's called Kafka Topics with partitions, but they're pretty similar. In Data Streams, though, you can do shard splitting and merging, so increase or decrease the throughput of your data stream. Whereas in Amazon MSK, scaling is a little bit harder, and you can only add partitions to a topic. You cannot remove partitions from a topic. In terms of encryption, Kinesis Data Streams has TLS in-flight encryption by default enabled, whereas for Amazon MSK, you have the option to choose to send the data over plain text, so no encryption, or TLS in-flight encryption as well. You get KMS at-rest encryption for both services. And in terms of security, you have IAM policies for authorization and authentication on the Kinesis Data Stream side. And for security on the Amazon SK, you can get mutual TLS for authentication and Kafka ACLs for authorization. That's combo number one. Or SASL Scram for authentication and Kafka ACLs for authorization. That's number two. Or IAM access control to do both authorization and authentication within MSK as well. So you have to choose one of these options. So that's it for this lecture. I hope it will help you gain some valuable points at the exam, and I will see you in the next lecture.